Welcome to the Sleepless Universe. In this video, we're going to explore the strangest planets we know, mysterious worlds that defy our understanding of reality. If you enjoy this kind of content, I'd really appreciate a like and subscribe. Also, feel free to share in the comments what time it is for you and where you're watching from. Now, I wish you a relaxing time and hope you enjoy this journey through the cosmos. HD 189733b, the Glass Rain Planet. In the vast expanse of our galaxy, approximately 63 light-years from Earth, exists a world so alien and hostile that it challenges our very understanding of what a planet can be. This gas giant orbits its star in the constellation Vulpecula, appearing as nothing more than a faint point of light to our telescopes. Yet this distant world harbors one of the most terrifying weather systems ever discovered. From a distance, this exoplanet might seem almost beautiful. Its deep azure color rivals that of Earth's oceans, creating an illusion of familiarity that quickly dissolves upon closer examination. This striking blue hue doesn't come from water or vast seas, but from something far more sinister. The atmosphere contains silicate particles that scatter blue light, much like our own sky. But these particles tell a story of unimaginable violence. This massive world belongs to a class of planets known as hot Jupiters. These gas giants orbit incredibly close to their parent stars, completing full rotations in mere days rather than years. In this case, one complete orbit takes just 2.2 Earth days. This proximity subjects the planet to intense stellar radiation, heating its atmosphere to temperatures exceeding 1,000 degrees Celsius. The extreme heat creates powerful atmospheric dynamics, unlike anything we experience on Earth. Winds rage across the surface at speeds reaching 7,000 kilometers per hour. To put this in perspective, the fastest winds ever recorded on Earth barely reach 400 kilometers per hour during the most severe hurricanes. These supersonic winds are more than 17 times faster than our planet's most extreme weather events. But speed alone doesn't capture the true horror of this planet's weather system. The intense heat and pressure in the atmosphere create conditions where silicate compounds exist as a gas. When these silicate particles condense in the cooler regions of the atmosphere, they form droplets of molten glass. These glass droplets then fall through the atmosphere as rain, but the fierce winds prevent them from falling straight down. Instead, the glass rain flies horizontally across the surface, propelled by those devastating 7,000 km/h winds. Imagine standing on this world and being pelted by molten glass moving at speeds that would make a bullet seem slow by comparison. The glass particles, heated to over 1,000 degrees Celsius, would be simultaneously melting and solidifying as they're hurled through the turbulent atmosphere. The close proximity to its star creates another fascinating phenomenon. This hellish planet is tidally locked, meaning one side permanently faces its star, while the other remains in eternal darkness. The day side experiences the full fury of stellar radiation, while the night side, though still incredibly hot by Earth standards, remains relatively cooler. This temperature difference drives the massive atmospheric circulation patterns that create those horizontal glass storms. Scientists discovered these extraordinary conditions through careful analysis of the light spectrum as the planet passes in front of its star. When the exoplanet transits across the face of its parent star, astronomers can analyze how the starlight filters through the atmosphere. Different chemical compounds absorb specific wavelengths of light, creating a fingerprint that reveals the atmospheric composition. The detection of silicate particles in the upper layers provided the first clues about the glass rain phenomenon. Further analysis revealed the extreme wind speeds through the Doppler effect, as different parts of the atmosphere move toward and away from Earth at different velocities. These measurements painted a picture of a world where the very air itself has become a weapon. The magnetic field of this gas giant, if it exists, would be constantly bombarded by charged particles from its nearby star. This stellar wind interaction could create auroras far more spectacular and dangerous than anything seen on Earth. The aurora would stretch across the entire globe, painting the glass-filled atmosphere with brilliant colors as charged particles collide with atmospheric gases. Understanding planets of this kind helps astronomers appreciate the incredible diversity of worlds that exist beyond our solar system. Each discovery reveals new possibilities for planetary formation and evolution, expanding our knowledge of how solar systems develop. These extreme environments serve as natural laboratories where physics operates under conditions impossible to recreate on Earth. The study of hot Jupiters like this one also provides insights into atmospheric dynamics on a massive scale. The heat transfer between the day and night sides of tidally locked planets creates circulation patterns that influence weather systems throughout the atmosphere. These processes, while extreme, follow the same fundamental physics that govern weather on Earth. The origin of this particular world tells a remarkable story of planetary migration. Scientists believe the gas giant originally formed much farther from its star, in the cooler outer regions where ice and gas could accumulate. Over millions of years, gravitational interactions caused the planet to spiral inward, eventually settling into its current extreme orbit just 4.5 million kilometers from its star. The star itself, a slightly smaller and cooler version of our Sun, bombards the nearby planet with radiation, creating surface temperatures hot enough to vaporize most known materials. This constant bombardment drives the complex chemistry that produces the silicate compounds responsible for the glass rain. Temperature variations across the world are extreme. The day side reaches temperatures of approximately 1,200 degrees Celsius, while the night side remains around 800 degrees Celsius. This temperature gradient drives massive atmospheric circulation patterns, creating jet streams that transfer energy from the day side to the night side in a perpetual cycle. The glass rain phenomenon occurs through continuous condensation and evaporation. Silicate particles rise through the atmosphere on powerful convection currents, existing as gas in the upper layers before condensing into glass droplets in cooler regions. These droplets are then swept up by the supersonic winds, creating horizontal glass storms that rage across the entire surface. Observing this violent world requires sophisticated space-based telescopes and careful analysis of light spectra. When it transits across its star, astronomers can study how starlight filters through the atmosphere, revealing the chemical fingerprints of different compounds. The Hubble Space Telescope and Spitzer Space Telescope have been instrumental in detecting water vapor, methane, and carbon dioxide in the planet's atmosphere, alongside the silicate particles that create the glass rain. These observations continue to refine our understanding of this extraordinary world and its violent weather systems. As we continue to discover and study exoplanets, extreme places like this one remind us that the universe contains phenomena far beyond our everyday experience. In the gentle blue glow of this distant planet lies a realm where glass rains sideways through a superheated atmosphere, where winds move faster than sound, and where the very concept of weather takes on meanings we never imagined possible. 55 Cancri E, the Diamond Planet. 40 light-years away in the constellation Cancer, orbiting a sun-like star, exists a world that transforms our understanding of planetary composition and challenges everything we thought we knew about the materials that can form planets. This object represents one of the most valuable worlds ever discovered, not in terms of monetary worth, but in the profound insights it offers into planetary formation and the exotic chemistry possible in distant solar systems. This remarkable planet belongs to a class known as super-Earths, worlds larger than our own planet, but smaller than Neptune. The world in question has nearly twice Earth's radius and approximately 8 times its mass, creating a planet with significantly stronger gravitational pull than our home planet. Yet, despite its larger size, this body completes one full orbit around its star in just 18 hours, making its years shorter than a single day on Earth. The extraordinary speed of its orbit places this exotic world incredibly close to its parent star, just 2.3 million kilometers away. To put this distance in perspective, Mercury, the closest planet to our Sun, orbits at a distance of nearly 58 million kilometers. This proximity subjects the surface to intense stellar radiation, heating the day side to temperatures exceeding 2,000 degrees Celsius. What makes this super-Earth truly extraordinary lies in its composition. Spectroscopic analysis reveals that the planet contains an unusually high concentration of carbon relative to oxygen. In most planetary systems, including our own, oxygen is more abundant than carbon, leading to the formation of silicate rocks and water. However, in systems where carbon dominates, entirely different chemical processes take precedence. The carbon-rich nature of this world suggests that much of its interior may consist of diamond and graphite rather than the silicate minerals that comprise rocky planets like Earth. Under the extreme pressures found deep within such massive rocky planets, carbon atoms arrange themselves into the crystalline structure we know as diamond. The core and mantle could contain diamond formations on a scale that dwarfs anything found on Earth. Current models suggest that up to 1/3 of the planet's mass could be composed of diamond. This would create a world where diamond, one of the rarest and most precious materials on Earth, forms the basic building blocks of an entire planet. The diamond content alone would have a theoretical value exceeding the entire global economy by factors of millions, though such calculations remain purely academic, given the impossibility of mining a planet 40 light-years away. The formation of this carbon-rich super-Earth required a very specific set of circumstances. The original protoplanetary disk around its star must have contained more carbon than oxygen, a relatively rare condition in stellar formation. As the planet accreted material from this carbon-rich disk, the dominant chemistry favored the formation of carbon-based minerals rather than the oxygen-rich silicates common in our solar system. The extreme temperatures on the sun-facing side create fascinating surface conditions. That hemisphere, permanently turned toward the star due to tidal locking, experiences temperatures hot enough to melt most metals. Under these conditions, any surface diamond would likely exist in a superheated state, potentially forming a thin atmosphere of carbon vapor above a molten carbon surface. The night side presents equally intriguing possibilities. While still extremely hot by Earth standards, the cooler temperatures on the dark side might allow for more stable diamond formations. The temperature gradient between day and night sides could create unique geological processes, with carbon cycling between different phases as heat flows across the planet's surface. Recent observations using advanced space telescopes have detected evidence of a thin atmosphere surrounding this planet. This atmosphere appears to contain hydrogen and helium, along with traces of heavier elements. The presence of an atmosphere on such a close-orbiting planet is remarkable, as the intense stellar radiation should have stripped away most atmospheric gases long ago. The magnetic field interactions between the planet and its star create another layer of complexity. The rapid orbit and extreme proximity to the stellar body subject the planet to intense magnetic forces that could influence atmospheric retention and surface chemistry. These interactions might help explain how it maintains any atmosphere at all under such extreme conditions. Studying such an exotic exoplanet provides valuable insights into planetary diversity and the range of compositions possible in the cosmos. The discovery challenges our Earth-centric view of planetary formation and demonstrates that carbon-rich worlds may be more common than previously thought. Understanding these exotic compositions helps astronomers refine models of planetary formation and evolution. The techniques used to study this body represent cutting-edge astronomical methods. By measuring its mass through gravitational effects on the host star and its size through transit observations, scientists can calculate density. Combined with spectroscopic analysis of composition, these measurements paint a picture of a world unlike anything in our solar system. The host star itself contains a complex planetary system with 5 known planets. The diamond-rich super-Earth is the innermost world, while the other planets orbit at greater distances in more conventional arrangements. This system architecture provides additional clues about the formation, history, and migration patterns that led to the current configuration. The gravitational dynamics within the system create additional complexity for understanding the planet's evolution. The presence of multiple neighboring worlds, including a massive gas giant in the outer system, influences orbital mechanics and may have played a role in driving this body to its current extreme orbit. These gravitational interactions continue to shape the system today, potentially affecting atmospheric retention and internal heat distribution through tidal forces that compress and stretch the carbon-rich interior. Future observations of this glittering world will continue to refine our understanding of the planet. Advanced telescopes currently under development will provide more detailed atmospheric analysis and surface temperature mapping. These studies may reveal additional exotic chemistry and help determine whether similar carbon-rich worlds exist elsewhere in our galaxy. The existence of this diamond planet expands our conception of what constitutes a planet and demonstrates the incredible diversity of worlds that populate the universe. In the depths of space, orbiting a distant sun, lies a world where diamond forms the foundation of an entire planet, challenging our understanding of planetary science and revealing the exotic possibilities that await discovery among the stars. WASP-12b, the Dying Planet. In the constellation Auriga, approximately 871 light-years from Earth, unfolds one of the most dramatic and poignant stories in our galaxy. This gas giant planet is slowly being consumed by its own star in a cosmic dance of destruction that will ultimately lead to the planet's complete annihilation. This dying world offers astronomers a rare glimpse into the final stages of planetary existence and the extreme gravitational forces that can tear apart entire worlds. This object belongs to the class of hot Jupiter planets, gas giants that orbit extremely close to their parent stars. However, even among these extreme worlds, this one stands out for its proximity to stellar destruction. The planet completes one full orbit around its star in just 1.09 Earth days, racing through space at tremendous speeds while locked in a deadly embrace with its stellar companion. The orbital distance of only 3.4 million kilometers brings the planet perilously close to its star's surface. To understand this proximity, consider that our Sun has a radius of approximately 696,000 kilometers. This planet orbits its star at a distance of less than 5 stellar radii, placing it within what astronomers call the Roche limit. This invisible boundary marks the point where a star's gravitational forces overcome a planet's ability to hold itself together. The consequences of this extreme proximity are catastrophic for the doomed gas giant. Its outer atmosphere is being systematically stripped away by the star's intense gravitational pull and stellar radiation. Material from the upper layers streams toward the star in a continuous flow, creating a bridge of hot gas that connects the two celestial bodies. This process, known as atmospheric stripping, occurs at a rate that astronomers can actually observe and measure. Current estimates suggest a loss of approximately 189 billion tons of material every second. This staggering rate of mass loss means the planet is literally evaporating before our eyes, though on astronomical timescales. The material being stripped away consists primarily of hydrogen and helium, the main components of gas giant atmospheres, along with heavier elements that create spectacular light shows as they spiral into the star. The host star, classified as a G-type star similar to our Sun, but slightly more massive and hotter, plays the role of cosmic predator in this relationship. Its stronger gravitational field and higher surface temperature create the conditions necessary for atmospheric stripping. The star's magnetic field interacts with the ionized gas flowing from the planet, creating complex plasma dynamics that accelerate the destruction process. Temperature measurements reveal the extreme conditions on this doomed world. The day side, permanently facing the star due to tidal locking, reaches temperatures exceeding 2,500 degrees Celsius. These temperatures are hot enough to dissociate molecular hydrogen and ionize many elements, creating the plasma that flows so readily toward the hungry star. The gravitational interaction creates another fascinating phenomenon known as tidal heating. Just as Earth's moon creates ocean tides through gravitational forces, the star's gravity stretches and compresses the planet in a continuous cycle. This tidal flexing generates internal heat, contributing to its expansion and making atmospheric escape even more likely. Observations using space-based telescopes have revealed an extended atmosphere that forms a comet-like tail of escaping gas. This tail extends far beyond the normal atmospheric boundary, creating a visible stream of material flowing toward the star. Spectroscopic analysis of this escaping material provides insights into internal composition and the physics of atmospheric loss. The dying process follows a predictable but complex pattern. As mass is lost, the gravitational hold on the remaining atmosphere weakens, accelerating the loss rate. The planet gradually shrinks and becomes less dense, while continuing tidal heating maintains the high temperatures that drive atmospheric escape. This feedback loop ensures that the destruction process continues relentlessly. Computer models predict complete atmospheric loss within approximately 10 million years, a brief moment in astronomical terms. After stripping is complete, the solid core, if one exists, may continue orbiting the star as a bare remnant. However, even this core faces eventual destruction, as continued tidal forces and stellar evolution may ultimately cause it to spiral into the star itself. Studying such a doomed world provides valuable insights into stellar planetary interactions and the ultimate fate of close-orbiting planets. Similar processes may occur around other stars, though the specific conditions required for such dramatic atmospheric stripping are relatively rare. Understanding these extreme cases helps astronomers predict the evolution of other planetary systems and the long-term stability of exoplanets. The discovery and continued observation represent a triumph of modern astronomical techniques. Transit photometry revealed the planet's existence, while follow-up spectroscopic observations detected the atmospheric escape. Advanced computer modeling helps scientists understand the complex physics involved in the destruction process and predict the planet's future evolution. The magnetic field interactions with the star create additional complexity in the mass loss process. As ionized gas from the atmosphere encounters the star's magnetic field, it can be channeled along magnetic field lines, creating hotspots on the stellar surface where planetary material impacts. These interactions may influence the rate of mass loss and the specific pathways by which material flows from planet to star. Future observations will continue tracking the gradual destruction and may reveal new details about atmospheric stripping. Advanced telescopes currently under development will provide more precise measurements of mass loss rates and atmospheric composition, helping refine our understanding of how planets die in the gravitational embrace of their stars. The chemical composition of the escaping material reveals fascinating details about the internal structure. Spectroscopic analysis has detected not only hydrogen and helium, but also heavier elements like carbon, oxygen, and metals being stripped from the atmosphere. The presence of these heavier elements suggests that atmospheric loss is reaching deeper layers of the planet, potentially exposing material from the interior that was originally incorporated during formation billions of years ago. The story of this world serves as a cosmic reminder of the dynamic and sometimes violent nature of planetary systems. In the depths of space, this doomed planet continues its death spiral, offering astronomers a unique laboratory for studying extreme gravitational interactions and the ultimate limits of planetary survival in the hostile environment near a star. TRIS 2b, darker than coal. In the constellation Draco, approximately 750 light-years from Earth, exists a world that challenges our understanding of planetary atmospheres and light absorption. This exoplanet holds the distinction of being the darkest known planet in the universe, reflecting less than 1% of the light that reaches it from its parent star. This cosmic void absorbs light more effectively than charcoal, black paint, or any material found naturally on Earth, creating a world so dark it appears almost invisible against the backdrop of space. The planet belongs to the family of hot Jupiter planets, gas giants that orbit extremely close to their parent stars. This one completes one full orbit around its star in just 2.47 Earth days, maintaining a distance of only 5 million kilometers from its stellar companion. This proximity subjects the atmosphere to intense stellar radiation, heating the planet to temperatures exceeding 1,200 degrees Celsius on the day side. Despite receiving tremendous amounts of energy from its nearby star, this world appears almost completely black when observed through telescopes. Its albedo, which measures how much light a celestial body reflects, registers at less than 0.01. To put this in perspective, Earth reflects approximately 30% of the sunlight it receives, appearing as a bright blue marble when viewed from space. Even the moon, which appears relatively dark to our eyes, reflects about 12% of the light that hits its surface. The extreme darkness results from a unique atmospheric composition and the chemical processes occurring at high temperatures. The planet's atmosphere contains compounds that are exceptionally efficient at absorbing light across the entire visible spectrum. Titanium oxide and vanadium oxide, present in gaseous form due to the extreme heat, act as powerful light-absorbing agents that prevent photons from escaping back into space. These metallic compounds exist in a vaporized state throughout the atmosphere, creating clouds of light-absorbing particles that trap incoming stellar radiation. Unlike water clouds on Earth, which appear white because they scatter light, the metallic clouds on this planet absorb virtually all wavelengths of visible light. The result is an atmosphere that functions like a cosmic black hole for photons, swallowing light with remarkable efficiency. The temperature distribution creates fascinating atmospheric dynamics. The day side, permanently facing its star due to tidal locking, experiences the most extreme heating and contains the highest concentrations of vaporized metals. The night side, while still scorching hot by Earth standards, maintains slightly cooler temperatures that may allow for different chemical processes and atmospheric circulation patterns. Atmospheric circulation transports heat from the day side to the night side through powerful jet streams and convection currents. These circulation patterns redistribute the light-absorbing compounds throughout the atmosphere, ensuring that the entire planet maintains its characteristic darkness. The continuous mixing of atmospheric gases prevents the formation of clear regions that might allow light to escape. The discovery of this exoplanet's extreme darkness came through careful analysis of its thermal emissions. While the planet reflects almost no visible light, it does emit infrared radiation due to its high temperature. Space-based telescopes can detect this thermal emission, allowing astronomers to study the planet's properties despite its visible light invisibility. These observations revealed that it absorbs nearly all incoming starlight and re-emits the energy as heat. The parent star, known as TRES-2, is remarkably similar to our Sun in terms of mass, size, and temperature. This similarity makes the planet's extreme darkness even more intriguing, as it demonstrates that planetary atmospheres can develop radically different properties even when orbiting sun-like stars. The star provides a steady stream of photons that the planet's atmosphere hungrily devours, converting light energy into heat through molecular absorption processes. Chemical modeling of the atmosphere suggests that null light absorption occurs through multiple mechanisms operating simultaneously. Titanium oxide and vanadium oxide molecules absorb light through electronic transitions, while other compounds may contribute through vibrational and rotational absorption bands. The combination of these processes creates an atmospheric environment that is virtually opaque to visible light. The extreme conditions also prevent the formation of reflective atmospheric features that might increase the albedo. Unlike gas giants in our solar system, which have reflective cloud layers and atmospheric bands, this world's high temperatures keep potential cloud-forming materials in gaseous form. This absence of reflective clouds contributes to the remarkable darkness. Temperature measurements reveal that the atmosphere efficiently converts absorbed light into thermal energy. The equilibrium temperature, calculated based on the amount of stellar radiation received, closely matches observations of infrared emissions. This agreement confirms that the planet is indeed absorbing nearly all incoming light and converting it to heat through atmospheric processes. The study of this blackened exoplanet provides valuable insights into atmospheric chemistry under extreme conditions. The planet serves as a natural laboratory for understanding how metallic compounds behave in hot, dense atmospheres, and how these conditions affect light absorption properties. These studies have implications for understanding the atmospheric evolution of hot Jupiter planets and the diversity of atmospheric compositions possible in exoplanetary systems. Comparative studies with other hot Jupiters reveal the factors that contribute to extreme darkness. While many hot Jupiters have low albedos due to their high temperatures, this one represents the extreme end of the spectrum. The specific combination of atmospheric composition, temperature, and pressure creates conditions that maximize light absorption while minimizing reflection. The techniques used to study this planet demonstrate the sophistication of modern exoplanet research. By measuring the tiny changes in brightness as the planet passes behind its star, astronomers can determine how much light the planet reflects or emits. These eclipse observations require extraordinary precision, as the light variations are less than 0.1% of the star's total brightness. Future observations will continue to refine our understanding of this dark world and its unique atmospheric properties. Advanced space telescopes will provide more detailed spectroscopic analysis of thermal emissions, potentially revealing additional details about atmospheric composition and temperature structure. These studies may uncover new mechanisms of light absorption and expand our knowledge of extreme atmospheric chemistry. The magnetic field, if present, would interact with the stellar wind from its nearby star in complex ways. The planet's rapid orbital motion through the star's magnetic field could induce electrical currents in its conductive atmosphere, potentially affecting the distribution of metallic compounds and contributing to the uniform darkness observed across the surface. These magnetospheric interactions remain an active area of research, as understanding them could provide additional insights into atmospheric dynamics. The existence of this world challenges our preconceptions about planetary appearance and demonstrates the incredible diversity of atmospheric conditions possible in the universe. In the depths of space, this cosmic shadow continues its eternal orbit, absorbing starlight with unmatched efficiency, and reminding us that the universe contains wonders far beyond our everyday experience of light and darkness. HD 106906b, the rogue giant planet. In the southern constellation Crux, approximately 336 light-years from Earth, exists one of the most mysterious and isolated worlds ever discovered. This planet challenges our fundamental understanding of planetary formation and orbital mechanics by maintaining a stable orbit at an extraordinary distance from its parent star. This massive object orbits 650 times farther from its star than Earth orbits the Sun, creating a cosmic puzzle that has forced astronomers to reconsider how planetary systems form and evolve. The planet represents an extreme example of a wide-orbit world, maintaining a distance of approximately 97 billion kilometers from its host star. To comprehend this vast separation, consider that Pluto, the most distant recognized dwarf planet in our solar system, orbits at an average distance of only 5.9 billion kilometers from the Sun. This world exists in a realm so distant that it receives virtually no heat from its star, creating conditions more akin to the cold depths of interstellar space than a traditional planetary environment. This isolated giant is a massive world, containing approximately 11 times the mass of Jupiter, our solar system's largest planet. This substantial mass places it on the boundary between planet and brown dwarf, those mysterious objects sometimes called failed stars. The planet's size and isolation raise fundamental questions about its origin and the processes that could create such an unusual celestial arrangement. Temperature measurements reveal a world existing in perpetual deep freeze. With surface temperatures estimated at -230 degrees Celsius, the planet receives virtually no warming from its distant star. Instead, any heat it possesses comes primarily from leftover energy from its formation billions of years ago, slowly radiating away into the cosmic void. This internal heat source allows it to emit just enough infrared radiation for astronomers to detect and study it. The host star is a young, hot binary system consisting of two stars orbiting each other. These stars are significantly more massive and luminous than our Sun, yet even their combined energy output provides negligible heating to the distant planet. The binary nature of the central star system adds another layer of complexity to understanding how this object could have formed and maintained its current orbit. Current theories about its origin fall into several competing categories, each attempting to explain how such a massive object could exist at such an enormous distance from its star. One possibility suggests that it formed much closer to its star through conventional accretion processes, then was subsequently ejected to its current distant orbit through gravitational interactions with other objects in the system. Alternative formation theories propose that the planet formed through direct gravitational collapse of a dense region within the original protoplanetary disk, similar to how stars form, but on a smaller scale. This process, called gravitational instability, could potentially create massive planets at large distances from their host stars without requiring migration from inner regions of the system. The gravitational dynamics of the system reveal additional complexity that may explain the unusual orbit. Observations have detected a debris disk surrounding the central binary star, containing dust and rocky material left over from the system's formation. The gravitational influence of this distant world may play a crucial role in shaping this debris disk, creating gaps and asymmetries in the distribution of material. Computer simulations suggest that the orbit may not be perfectly stable over long timescales. The combined gravitational influences of the binary star system and passing nearby stars could gradually alter the planet's orbital parameters, potentially causing it to migrate even farther from its host stars, or, conversely, to spiral inward over millions of years. The age of the system, estimated at approximately 15 million years, provides important clues about planetary formation timescales. This relatively young age suggests that the planet formed relatively recently in cosmic terms, offering astronomers a glimpse into the early stages of planetary system evolution. The planet's current properties may reflect conditions that existed during the chaotic early period of system formation. Atmospheric studies remain challenging due to the planet's great distance from Earth and its faint infrared emissions. However, spectroscopic analysis has revealed the presence of water vapor and carbon monoxide in the atmosphere, compounds that remain gaseous even at extremely low temperatures. These atmospheric constituents provide insights into the formation environment and chemical evolution of the world. The discovery required advanced direct imaging techniques, as the orbital separation allows the planet to be resolved as a distinct point of light separate from its host stars. This achievement represents a significant milestone in exoplanet detection capabilities, as most known exoplanets are discovered through indirect methods that rely on their gravitational or transit effects on their host stars. Comparative studies between this object and similar wide-orbit planets in other systems help astronomers understand the frequency and characteristics of these unusual worlds. The growing catalog of directly imaged exoplanets reveals that wide-orbit giant planets may be more common than previously thought, suggesting that planetary formation processes can operate effectively even at large distances from stars. The magnetic field, if present, would operate under unique conditions due to the planet's isolation and low temperature. Unlike hot Jupiters that experience intense stellar radiation, this planet's magnetic field would interact primarily with the interstellar medium and cosmic rays, potentially creating aurora phenomena visible across a wide range of electromagnetic wavelengths. The long-term evolution of this distant giant depends on several factors, including the stability of its orbit and the evolution of its host binary star system. As the central stars age and evolve, their gravitational influence may change, potentially affecting orbital stability. Additionally, encounters with passing stars or other gravitational perturbations could alter the planet's trajectory over millions of years. Future observations will focus on refining measurements of its orbital parameters and atmospheric composition. Advanced space telescopes currently under development will provide more detailed spectroscopic analysis and may reveal additional atmospheric constituents or surface properties. These studies will help determine whether the planet possesses moons or ring systems and provide insights into its internal structure. The existence of this distant object expands our understanding of the diversity possible in planetary systems and demonstrates that giant planets can form and survive at distances previously thought impossible. This isolated world serves as a natural laboratory for studying planetary atmospheres under extreme conditions, and provides valuable insights into the complex processes that shape planetary system architecture across the universe. Kepler 16b, the Tatooine planet. In the constellation the Cygnus, approximately 245 light-years from Earth, exists a world that transforms science fiction into scientific reality. This planet orbits not one star, but two, creating a planetary system that mirrors the iconic twin-sun world of Tatooine from Star Wars. This remarkable object represents the first confirmed discovery of a circumbinary planet, a world that maintains a stable orbit around a binary star system while experiencing the complex gravitational dance of two stellar companions. This world completes one full orbit around its binary star system every 229 Earth days, maintaining an average distance of approximately 104 million kilometers from the center of mass of the two stars. This orbital distance places it in a region where it experiences the combined gravitational influence of both stars, creating unique orbital mechanics that differ significantly from planets in single-star systems like our own solar system. The two stars at the heart of this system present a study in stellar contrasts. The primary star contains approximately 69% of our Sun's mass and shines with about 20% of our Sun's luminosity. Its companion is significantly smaller and dimmer, containing only 20% of our Sun's mass and producing less than 1% of our Sun's light output. These two stars orbit each other every 41 days, locked in a gravitational embrace that creates a constantly changing illumination pattern for their distant planetary companion. The binary nature of the system creates fascinating lighting conditions on the planet's surface. Unlike Earth, which receives steady illumination from a single star, this gas giant experiences a complex cycle of illumination that depends on the relative positions of both stars and the planet's location in its orbit. During certain periods, both stars appear in the sky simultaneously, creating a double-star sunrise or sunset that would rival any science fiction visualization. This Saturn-like world contains approximately 105 times Earth's mass and has a radius about 8.5 times larger than Earth's radius. Its composition likely consists primarily of hydrogen and helium, with possible traces of heavier elements in its atmosphere and a rocky or icy core buried deep within its gaseous envelope. Temperature measurements reveal that the planet exists in a perpetually cold environment, with surface temperatures estimated between -73 and -101 degrees Celsius. This frigid climate results from its distance from the stars and the relatively low luminosity of the stellar pair. The combined energy output provides insufficient heating to create temperate conditions on the distant world. The gravitational dynamics create unique tidal effects. Unlike planets orbiting single stars, which experience relatively simple tidal forces, this one must contend with the combined and constantly changing gravitational influences of two stars. These complex tidal interactions may contribute to internal heating within the planet through tidal flexing, similar to the processes that heat Jupiter's moon, Io, in our solar system. Discovery of the object required sophisticated analysis of light variations detected by the Kepler Space Telescope. It reveals its presence through transit events, periodically passing in front of one or both of its host stars as viewed from Earth. However, unlike simple planetary transits around single stars, the timing and depth of these transits vary significantly due to the complex orbital mechanics of the three-body system. The orbital stability represents a remarkable achievement of celestial mechanics. In a binary star system, there are specific regions where planetary orbits can remain stable over long periods. This gas giant orbits in what astronomers call the circumbinary habitable zone, though its gas composition and cold temperatures make it unsuitable for life as we know it. However, any large moons orbiting the planet might potentially maintain more temperate conditions. The binary stars exhibit different spectral types, with the primary classified as a K-type star and the secondary as an M-type red dwarf. This combination creates a unique stellar environment where the planet receives light across different wavelengths and intensities. The varying stellar output as the two stars orbit each other creates seasonal variations in the planet's energy input that have no parallel in single-star systems. Atmospheric modeling suggests that the planet's atmosphere would exhibit complex circulations patterns driven by the variable stellar heating. The constantly changing illumination from the binary stars would create atmospheric dynamics, unlike those found on planets orbiting single stars. These circulation patterns might produce unique weather systems and atmospheric phenomena that reflect the dual-star environment. The formation of the planet presents interesting challenges for planetary formation theories. It likely formed from the same protoplanetary disk that surrounded the binary star system during its early evolution. However, the gravitational perturbations from two stars would have significantly influenced the accretion process, potentially affecting the timing and efficiency of planetary formation compared to single-star systems. Eclipse events in the system provide additional opportunities for scientific observation. When one star passes in front of the other, it creates stellar eclipses that allow astronomers to study the properties of both stars in detail. These eclipsing binary observations, combined with planetary transit data, create a wealth of information about the system's architecture and evolution. The magnetic field interactions in the binary system would be particularly complex, involving the magnetic fields of both stars and potentially the planet itself. The binary stars' magnetic fields would interact with each other and with any planetary magnetic field, creating a dynamic magnetospheric environment. These interactions might produce aurora phenomena on the planet that reflect the dual star influence. Seasonal variations would follow patterns completely different from those experienced on Earth. The planet's seasons would depend not only on its orbital position relative to the binary star pair, but also on the orbital phase of the two stars around each other. This creates a complex seasonal cycle that repeats every 229 Earth days, but with significant variations based on the 41-day stellar orbital period. The discovery opened a new field of exoplanet research focused on circumbinary planets. Subsequent discoveries of similar worlds have revealed that planets can indeed form and survive in binary star systems, expanding our understanding of planetary system diversity. These findings suggest that binary star systems, which comprise a significant fraction of all stellar systems, may commonly host planetary companions. Future observations will focus on refining atmospheric models and searching for potential moons that might orbit this gas giant. Advanced telescopes may eventually provide direct spectroscopic observations of its atmosphere, revealing chemical composition and atmospheric dynamics. These studies will enhance our understanding of how planets evolve in the complex gravitational environment of binary star systems. The existence of this Saturn-sized planet demonstrates that the universe contains planetary environments far more diverse and exotic than early astronomers imagined. This real-world Tatooine reminds us that science often surpasses fiction in revealing the remarkable variety of worlds that populate our galaxy, each with its own unique characteristics shaped by the specific conditions of its stellar environment. Gliese 581c, potentially habitable yet extreme. In the constellation Libra, just over 20 light-years from Earth, exists a world that has captivated astronomers and sparked intense debate about the possibilities for life beyond our solar system. This planet occupies a unique position in exoplanet research as one of the first discovered worlds located within its star's habitable zone, that precious region where liquid water might exist on a planetary surface. Yet this potentially life-supporting world harbors extreme conditions that challenge our understanding of habitability and planetary climate dynamics. The planet orbits a red dwarf star, completing one full revolution every 13 Earth days, at a distance of approximately 11 million kilometers from its stellar companion. This close proximity places it well within what astronomers initially calculated as the habitable zone, around the relatively cool red dwarf. The concept of a habitable zone, sometimes called the Goldilocks zone, represents the orbital distance where temperatures are neither too hot nor too cold for liquid water to exist on a surface. Classified as a super-Earth, this object contains approximately 5 times the mass of our home planet and possesses a radius roughly 1.5 times larger than Earth's. This increased mass creates a gravitational field significantly stronger than Earth's, with surface gravity estimated at nearly twice what humans experience. Such intense gravitational conditions would profoundly affect atmospheric dynamics, weather patterns, and the potential for any life forms that might exist on the surface. The planet orbits so close to its star that it has become tidally locked, meaning one hemisphere permanently faces the star while the other remains in eternal darkness. This configuration creates extreme temperature variations across the surface, with the day side potentially experiencing scorching heat, while the night side freezes in perpetual winter. The boundary region between these extremes, known as the terminator zone, represents the most temperate area on the planet. The red dwarf star presents both opportunities and challenges for planetary habitability. These stars are significantly cooler and less luminous than our Sun, requiring planets to orbit much closer to receive adequate energy for liquid water. However, red dwarfs are also known for their stellar activity, including powerful flares that can strip away planetary atmospheres and bombard nearby worlds with harmful radiation. Initial atmospheric modeling suggested the possibility of a dense carbon dioxide atmosphere that could create a greenhouse effect, strong enough to maintain liquid water on parts of the surface. However, more detailed climate simulations have revealed the complex interplay between atmospheric composition, stellar radiation, and planetary rotation that determine surface conditions on tidally locked worlds. The greenhouse effect on this super-Earth could operate quite differently from the familiar process on Earth. A dense atmosphere might trap enough heat to transport thermal energy from the day side to the night side through atmospheric circulation, potentially moderating the extreme temperature differences. Alternatively, a runaway greenhouse effect could create surface conditions similar to those found on Venus, with temperatures hot enough to boil away any liquid water. Atmospheric escape represents another significant challenge for habitability. The proximity to the star subjects the atmosphere to intense stellar wind and radiation that could gradually strip away gases over geological timescales. The strength of the magnetic field, if present, would play a crucial role in protecting the atmosphere from erosion by charged particles from the stellar wind. The composition of this world remains largely unknown, but its classification as a super-Earth suggests it could be either a rocky planet with a thick atmosphere or a mini-Neptune with a substantial gaseous envelope surrounding a solid core. The bulk density, calculated from its mass and radius, indicates a composition that could support either interpretation, leaving fundamental questions about its nature unresolved. Water, if it exists, would likely be confined to specific regions determined by local temperature and atmospheric conditions. The terminator zone, where day meets night, might harbor the most stable liquid water reservoirs. Alternatively, if atmospheric circulation effectively redistributes heat, larger regions of the planet might maintain temperatures suitable for the existence of liquid water. The intense gravitational field would significantly affect atmospheric dynamics and weather patterns. The stronger gravity would create denser atmospheric layers and could influence the development of storm systems and circulation patterns. These effects might actually help stabilize conditions by preventing the loss of atmospheric gases to space while promoting efficient heat distribution across the surface. Stellar flares from the red dwarf pose ongoing threats to atmospheric stability and potential habitability. These energetic events can increase the star's brightness by several times its normal output and emit intense bursts of ultraviolet radiation and charged particles. Repeated flare events over millions of years could gradually erode the atmosphere and sterilize the surface through radiation exposure. The age of the system, estimated at several billion years, provides both advantages and challenges for habitability. The system's maturity suggests that any initial period of intense stellar activity has likely subsided, potentially allowing for more stable atmospheric conditions. However, the long time span also increases the cumulative effects of atmospheric erosion and radiation exposure. A magnetic field, if present, would provide crucial protection against stellar radiation and atmospheric loss. The planet's larger mass and potentially molten core could generate a magnetic field stronger than Earth's, offering better protection against stellar wind and radiation. However, the close orbital distance places the planet well within the reach of its star's magnetic influence, creating complex interactions that could affect atmospheric retention. Climate modeling continues to evolve as scientists develop more sophisticated understanding of atmospheric processes on tidally locked worlds. Three-dimensional climate simulations reveal the complex interplay between stellar heating, atmospheric circulation, and surface conditions that determine whether liquid water can exist and persist over geological timescales. The search for atmospheric signatures represents an ongoing challenge due to the planet's distance from Earth and the limitations of current observational techniques. Future space telescopes may eventually provide direct spectroscopic observations of the atmosphere, if it possesses one, revealing its chemical composition and providing definitive answers about its potential habitability. Comparative studies between this planet and other super-Earths in the habitable zones of red dwarfs help astronomers understand the factors that promote or inhibit habitability on these common types of exoplanets. The growing catalog of discoveries provides valuable context for interpreting the properties and potential of worlds like this one. The legacy of this enigmatic object extends beyond its individual characteristics to its role in advancing our understanding of planetary habitability and the diversity of potentially life-supporting worlds in our galaxy. This extreme and mysterious planet continues to challenge our assumptions about where life might arise and reminds us that habitability depends on a complex interplay of factors that we are only beginning to understand. WASP-17b, the backwards planet. In the constellation Scorpius, approximately 1,000 light-years from Earth, orbits one of the most perplexing worlds ever discovered. This gas giant defies conventional understanding of planetary formation and orbital mechanics by traveling in retrograde motion around its parent star. While most planets orbit in the same direction as their star's rotation, this one rebelliously moves in the opposite direction, creating a cosmic puzzle that has forced astronomers to reconsider fundamental principles of how planetary systems form and evolve. This object belongs to the class of hot Jupiter planets, gas giants that orbit extremely close to their parent stars. It completes one full orbit every 3.73 Earth days, maintaining a distance of approximately 7.5 million kilometers from its stellar companion. This proximity subjects the atmosphere to intense stellar radiation, heating it to temperatures exceeding 1,500 degrees Celsius, and causing the planet to become inflated to nearly twice the radius of Jupiter, despite containing only half of Jupiter's mass. The retrograde orbit represents a fundamental departure from the standard model of planetary system formation. In conventional scenarios, planets form from a rotating disk of gas and dust surrounding a young star, with both the star and planets naturally rotating and orbiting in the same direction. The discovery of this backwards motion suggests that dramatic gravitational interactions must have occurred sometime after the planet's initial formation. Several mechanisms could potentially explain how this object acquired its retrograde orbit. One possibility involves gravitational interactions with other massive bodies in the system, such as additional planets or stellar companions. These interactions could have gradually altered the orbital inclination over millions of years, eventually flipping the orbit to move contrary to the star's rotation. Alternatively, close encounters with passing stars might have disrupted the original orbital configuration. The Kozai mechanism represents another potential explanation for the unusual orbit. This gravitational process occurs in systems with multiple massive objects and can cause periodic oscillations in a planet's orbital eccentricity and inclination. Over long timescales, these oscillations might drive the orbit to extremely high inclinations, potentially resulting in retrograde motion around the host star. Tidal interactions between this hot Jupiter and its star create unique consequences due to the retrograde motion. Unlike planets in prograde orbits, where tidal forces gradually slow orbital motion and cause inward spiraling, retrograde planets experience tidal effects that can actually accelerate orbital decay. This suggests a faster trajectory toward eventual destruction as the planet spirals into its parent star. The extreme inflation of this world adds another layer of complexity. Its low density, approximately 1/7 that of Jupiter, indicates that the atmosphere has expanded significantly beyond normal proportions. The combination of intense stellar heating and possible tidal heating from retrograde orbital motion may contribute to this dramatic atmospheric expansion. Atmospheric studies reveal the presence of water vapor, carbon monoxide, and other molecular species in the extended atmosphere. The low surface gravity, due to the inflated nature, creates atmospheric conditions quite different from more typical hot Jupiters. The reduced gravitational binding allows gases to extend farther from the surface, forming an expanded envelope that may be gradually escaping into space. The host star, an F-type star slightly more massive and hotter than our Sun, creates an intense radiation environment that bathes the close orbiting planet in high-energy photons. The interaction between this stellar radiation and the planet's extended atmosphere drives complex photochemical processes that affect atmospheric composition and structure. Temperature mapping reveals significant variations across the surface due to the tidally locked nature. The day side, permanently facing the star, reaches extreme temperatures that dissociate molecular hydrogen and ionize atmospheric gases. The night side, while still extremely hot by Earth standards, maintains cooler temperatures that allow for different chemical processes and atmospheric dynamics. The magnetic field, if present, would operate under unusual conditions due to the retrograde orbit. The relative motion between the planet and stellar magnetic field creates unique magnetospheric interactions that differ from those experienced by planets in prograde orbits. These interactions could affect atmospheric retention and create distinctive aurora phenomena in the upper atmosphere. Atmospheric circulation patterns are influenced by both intense stellar heating and the unusual orbital characteristics. The retrograde motion affects the Coriolis forces that shape circulation, potentially creating wind patterns and jet streams that differ from those found on planets with conventional orbital orientations. These circulation patterns redistribute heat and influence atmospheric chemistry. The discovery of the retrograde orbit required careful analysis of the Rossiter-McLaughlin effect, a subtle spectroscopic signature that reveals the relative motion between a transiting planet and its rotating star. During transits, the planet blocks different portions of the stellar surface that are moving toward or away from Earth due to rotation. The resulting spectroscopic variations reveal the alignment between orbital motion and stellar spin. Long-term evolution models predict a complex future influenced by retrograde motion and proximity to the star. The enhanced tidal interactions may cause a more rapid inward spiral than typical hot Jupiters, potentially leading to atmospheric stripping and eventual destruction. The timescales for these processes depend on internal structure and the strength of tidal dissipation mechanisms. The inflated nature may result from several heating mechanisms working in combination. Intense stellar irradiation provides the primary energy source, while tidal heating from a slightly eccentric orbit contributes additional internal heating. Retrograde orbital motion may enhance these effects through complex gravitational interactions with the star's tidal bulge. Comparative studies with other hot Jupiters help astronomers understand the factors that influence planetary inflation and atmospheric escape. The extreme properties place this world at one end of the hot Jupiter spectrum, providing valuable insights into the physical processes that govern such exotic planets under extreme conditions. The atmospheric escape rate may be enhanced by low surface gravity and the extended envelope. Hydrodynamic escape models suggest that the planet could be losing atmospheric material at significantly higher rates than more compact hot Jupiters. This ongoing mass loss may eventually strip away the extended atmosphere, revealing a denser core beneath. Future observations will focus on refining atmospheric composition measurements and tracking changes in the planet's properties over time. Advanced space telescopes may detect temporal variations in escape rates or compositional shifts that reflect the ongoing evolution of this remarkable world. The existence of this retrograde hot Jupiter demonstrates that planetary systems can undergo dramatic evolutionary changes that reshape their architecture in unexpected ways. This backwards world serves as a reminder that the universe contains phenomena that challenge our preconceptions and expand our understanding of the complex gravitational processes that govern planetary system evolution throughout the cosmos. HD 80606b, the temperature shock planet. In the constellation Ursa Major, approximately 190 light-years from Earth, exists a world that experiences the most extreme temperature variations of any known planet. This gas giant follows a highly eccentric orbit that carries it on a dramatic journey from the cold depths of its outer solar system to a scorching close encounter with its parent star. This cosmic roller coaster creates temperature swings of over 500 degrees Celsius in just a few hours, subjecting the atmosphere to thermal shock events that dwarf any weather phenomena found elsewhere in the known universe. This object belongs to the class of eccentric hot Jupiters, gas giant planets whose highly elliptical orbits create extreme variations in stellar heating throughout their orbital periods. Its orbit resembles a stretched ellipse, carrying it from a distant aphelion of approximately 129 million kilometers from its star to a close periastron approach of just 4.4 million kilometers. This dramatic orbital variation means the planet alternately experiences conditions similar to those between Earth and Mars, then suddenly plunges to distances closer than Mercury's orbit around our Sun. It completes one full orbital revolution every 111 Earth days, spending most of this time in the cold outer regions of its eccentric path. For approximately 100 days of each orbit, the planet maintains a relatively stable, frigid environment, with temperatures hovering around -200 degrees Celsius. During this extended winter phase, it receives minimal energy from its distant star and exists in conditions similar to the outer regions of our solar system. The drama begins as the planet approaches Periastron, its closest point to the star. Over the course of just a few days, the distance from the star decreases rapidly, causing an exponential increase in the amount of stellar radiation it receives. The intensity of stellar heating follows an inverse square law, meaning that halving the distance quadruples the energy input. As this gas giant swoops toward its star, this relationship creates a runaway heating effect that transforms the atmosphere in mere hours. During Periastron passage, the dayside temperature skyrockets from approximately -200 degrees Celsius to over 500 degrees Celsius in less than 6 hours. This represents one of the most rapid planetary heating events ever observed, with temperature rise rates exceeding 80 degrees Celsius per hour. The thermal shock creates atmospheric conditions that change faster than weather systems can adapt, resulting in extreme atmospheric dynamics and chemistry. The highly eccentric orbit results from complex gravitational interactions within the system. The primary star has a binary companion located at a considerable distance. The gravitational influence of this stellar companion likely played a role in shaping the unusual orbit through a process called Kozai oscillations, which can drive planetary orbits to high eccentricities over millions of years. Atmospheric modeling reveals the extraordinary challenges faced by the gaseous envelope during each orbital cycle. The rapid temperature increase during Periastron passage creates powerful convection currents and atmospheric expansion that fundamentally alter the structure. The atmosphere must continuously adapt to wildly varying energy inputs, creating circulation patterns unlike those found on any other known world. The thermal properties of the atmosphere play a crucial role in how the planet responds to these extreme temperature variations. Heat capacity and thermal conductivity determine how quickly temperature changes propagate through different layers. Gas giant atmospheres typically have relatively low thermal conductivity, meaning that rapid surface heating may not immediately affect deeper layers. During the brief Periastron passage, tidal forces may contribute additional heating through tidal flexing. The proximity to the star during this phase subjects the planet to strong differential gravitational forces that stretch and compress its interior. This tidal heating adds to the already extreme thermal input from stellar radiation, potentially contributing to atmospheric expansion and dynamic behavior. The cooling phase following Periastron represents another extreme aspect of the thermal cycle. As the planet rapidly recedes from its star, the intense heating source diminishes quickly, leaving the superheated atmosphere to radiate excess energy into space. The cooling rate depends on radiative properties and the efficiency of heat redistribution through atmospheric circulation. Observational studies have captured real-time measurements of temperature variations during Periastron passage. Space-based infrared telescopes can detect thermal emission from the dayside, revealing dramatic temperature changes as they occur. These observations provide unprecedented insights into how planetary atmospheres respond to extreme and rapidly changing thermal conditions. Atmospheric chemistry undergoes dramatic transformations during each thermal cycle. Extreme temperature variations drive chemical reactions and phase changes that continuously alter composition. Molecules that remain stable during the cold phase may dissociate or ionize during the hot phase, only to recombine as the planet cools again. Wind patterns likely exhibit extreme variability corresponding to the orbital cycle. During the cold phase, atmospheric circulation may be relatively calm, driven primarily by internal heat sources and rotation. However, rapid heating during Periastron would create powerful pressure gradients that drive supersonic winds and turbulent mixing. The magnetic field, if present, would experience significant stress during each orbital cycle. Rapid changes in atmospheric conductivity and the intense stellar wind encountered during Periastron passage could induce electrical currents and magnetic field variations. These magnetospheric dynamics might contribute to additional heating through Joule heating and magnetic reconnection events. Long-term evolution models suggest that extreme thermal cycling may gradually affect atmospheric retention and internal structure. Repeated heating and cooling cycles could drive atmospheric escape, particularly of lighter elements, potentially altering the composition over geological timescales. Ongoing tidal interactions may also affect orbital evolution. The atmospheric escape rate likely varies dramatically throughout the orbital cycle. During periastron, the combination of high temperatures and intense radiation creates conditions favorable for hydrodynamic escape, where atmospheric gases reach sufficient velocities to overcome gravitational binding. The cold phase may see minimal loss, creating a cyclical pattern of atmospheric retention and escape. Comparative studies with other eccentric planets help astronomers understand the factors that control atmospheric dynamics under extreme conditions. This planet serves as a natural laboratory for studying atmospheric physics under conditions impossible to replicate in terrestrial laboratories, providing insights into gas behavior under rapid thermal cycling. The discovery and study of this remarkable world have advanced our understanding of planetary atmospheric dynamics and the effects of orbital eccentricity on climates. This temperature-shocked gas giant demonstrates the incredible diversity of environmental conditions that can exist on exoplanets and highlights the complex interplay between orbital mechanics and atmospheric physics. Future observations will continue to refine our understanding of its extreme thermal behavior and may reveal additional details about atmospheric composition changes during thermal cycling. Advanced spectroscopic techniques may detect molecular species that appear and disappear as the planet undergoes its dramatic temperature variations, providing further insights into the chemistry of this remarkable world. Kepler 70b, the surviving Hell planet. In the constellation the Cygnus, approximately 3,850 light-years from Earth, orbits one of the most extraordinary survivors in the known universe. This planet circles its parent star in the impossibly short period of just 5.76 hours, completing more than 4 full orbits every Earth day. This remarkable world represents one of the closest planetary orbits ever discovered and tells a dramatic story of survival against overwhelming odds in the aftermath of stellar death and rebirth. It maintains an orbital distance of merely 760,000 kilometers from its star, placing it closer to its stellar companion than the Moon is to Earth. At this extreme proximity, the planet experiences gravitational forces and stellar radiation, unlike anything found elsewhere in our galaxy. The intense tidal forces from its nearby star have almost certainly locked its rotation, creating a dayside that perpetually faces the stellar furnace and a nightside trapped in eternal darkness. The parent star presents a cosmic puzzle that makes this planetary system truly unique. Classified as a subdwarf B star, it belongs to a rare type of stellar remnant that forms through unusual evolutionary pathways. These stars represent objects that have shed their outer layers and exposed their hot, helium-burning cores to space. They burn at extremely high temperatures, often exceeding 20,000 degrees Celsius at their surface. The formation story of this system involves one of the most dramatic events possible in stellar evolution. The star likely began as a normal main-sequence star similar to our Sun, but evolved into a red giant phase where it expanded to enormous proportions. During this red giant phase, the star's outer layers would have engulfed any close-orbiting planets, seemingly destroying them in the stellar furnace. However, this planet somehow survived the catastrophic event, emerging from the stellar interior as the star shed its outer layers and contracted into its current configuration. Its survival suggests either an extraordinary resilience to extreme conditions or a complex orbital evolution that allowed it to avoid complete destruction during the red giant phase. Current surface temperatures reach approximately 6,900 degrees Celsius on the day side, making it one of the hottest planetary surfaces ever discovered. These temperatures exceed those found on many stellar surfaces and approach the levels required for nuclear fusion reactions. The night side, while receiving no direct stellar radiation, likely maintains temperatures of several thousand degrees due to atmospheric heat redistribution and tidal heating. The extreme temperatures create surface conditions where most materials exist in gaseous or plasma states. Any rocky surface material would be completely vaporized, creating an atmosphere of rock vapor and ionized metals. The atmosphere, if it can be called that, likely consists of silicon, iron, magnesium, and other heavy elements in gaseous form. creating a hellish environment unlike anything in our solar system. Atmospheric escape represents a constant process due to the extreme temperatures and proximity to the star. Surface gravity, while strong enough to retain some atmospheric material, faces continuous bombardment from stellar radiation and stellar wind that drives particles to escape velocities. The planet is likely losing mass continuously, though at rates that allow it to persist over astronomical timescales. The discovery challenged existing theories about planetary survival during stellar evolution. Traditional models suggested that planets orbiting within a few astronomical units of their parent stars would be destroyed when those stars evolved into red giants. The existence of this world demonstrates that some planets can survive even the most extreme stellar evolutionary events. Tidal heating plays a significant role in maintaining extreme temperatures. The close orbit subjects the planet to powerful tidal forces that continuously deform its shape. This tidal flexing generates internal heat through friction and contributes to the planet's overall thermal budget, supplementing the intense stellar heating from its nearby companion. The magnetic field environment would be extremely complex and dynamic. Rapid orbital motion through the star's magnetic field would induce powerful electrical currents in the conductive atmosphere. These currents could generate their own magnetic fields and create intense aurora phenomena visible across the entire electromagnetic spectrum. Orbital dynamics calculations suggest that the orbit may not be perfectly stable over very long timescales. Intense tidal interactions between the planet and star could cause gradual orbital decay, potentially leading the planet to spiral into its stellar companion over millions of years. Alternatively, stellar evolution effects might cause the orbit to gradually expand as the star loses mass. The companion planet in the system, orbiting slightly farther from the star with a period of 8.2 hours, provides additional context. The presence of two planets in such close orbits suggests that the survival mechanism that preserved this hellish world may have operated on multiple planets in the system. Spectroscopic studies remain challenging due to the small size and extreme proximity to the bright, hot star. However, future observations may detect thermal emission from the day side or atmospheric signatures that reveal the composition of the rock vapor atmosphere. These studies could provide insights into planetary composition and atmospheric processes under the most extreme conditions imaginable. The existence of this object expands our understanding of planetary system evolution and demonstrates the remarkable resilience of some worlds to survive even the most catastrophic stellar events. This survivor serves as a testament to the diverse pathways of planetary evolution and the extreme environments that can exist in our universe. Long-term studies of the system may reveal additional details about how planets can survive stellar evolution and adapt to changing environments. The system provides a unique laboratory for studying planetary physics under conditions that push the boundaries of what we consider possible for planetary survival. The thermal equilibrium represents a delicate balance between energy input from stellar radiation and tidal heating versus energy loss through atmospheric escape and thermal radiation. The ability to maintain this equilibrium while experiencing such extreme conditions provides insights into planetary energy budgets under the most hostile environments imaginable. Computer models suggest that the internal structure may have been fundamentally altered by its passage through the red giant phase, potentially creating a differentiated core mantle structure, quite different from planets that formed under more conventional circumstances. The story of this planet reminds us that planetary systems can undergo dramatic transformations while still maintaining some semblance of their original architecture. This surviving world demonstrates that even in the face of stellar death and rebirth, some planets endure, forever changed, but still orbiting in the cosmic dance that began billions of years ago. J1407b, the ring giant planet. In the constellation Centaurus, approximately 434 light-years from Earth, exists a world that transforms our understanding of planetary ring systems and challenges the very limits of what we thought possible in terms of circumplanetary structures. This massive planet, often called a super Saturn, possesses a ring system so massive and extensive that it dwarfs Saturn's famous rings by a factor of 200. creating a cosmic spectacle that would dominate the sky of any nearby world and fundamentally alter our conception of planetary ring dynamics. The ring system surrounding this gas giant extends to a radius of approximately 90 million kilometers from the planet's center, spanning a distance equivalent to about 60% of the Earth-Sun separation. To visualize this immense scale, if Saturn's rings were enlarged to match this system, they would appear larger than the full moon when viewed from Earth. This colossal ring structure contains enough material to form several Earth-sized moons, representing one of the most massive circumplanetary disk systems ever discovered. The planet itself remains somewhat mysterious, as direct observations are extremely challenging due to its distance and the obscuring effects of the massive ring system. Current estimates suggest the world may contain 10 to 40 times the mass of Jupiter, placing it on the boundary between a massive gas giant planet and a brown dwarf star. Its young age, estimated at approximately 16 million years, indicates that both the planet and its ring system are still in the early stages of evolution. The discovery of the ring system came through analysis of unusual light variations from its parent star. Over a period of 56 days in 2007, the star's brightness dimmed by up to 95% in a complex pattern that could only be explained by an enormous ring system passing in front of the star. This transit event provided astronomers with detailed information about the ring structure, revealing multiple gaps and density variations throughout the system. The ring system exhibits a complex architecture with over 30 distinct ring segments separated by gaps of varying widths. These gaps likely result from gravitational interactions with embedded moonlets or proto-moons that are clearing their orbital paths through the ring material. The largest gap in the ring system spans approximately 20 million kilometers, suggesting the presence of a moon roughly the size of Earth that has swept its orbital zone clean of ring particles. The composition of the rings remains largely unknown, but they likely consist of a mixture of ice, rock, and dust, similar to other planetary ring systems, but on a vastly larger scale. The massive amount of material suggests the rings may have formed through the catastrophic disruption of large moons, or the capture of material from the surrounding protoplanetary disk during the system's early formation period. Temperature variations throughout the ring system create diverse environments for different types of particles and potential moon formation. The inner regions of the ring system, closer to the planet's heat, would favor rocky particles and dust, while the outer regions might contain significant amounts of water ice and other volatile compounds. These temperature gradients influence the chemical evolution and dynamics of the ring material. The gravitational dynamics within the system are extraordinarily complex due to the sheer scale and mass of the structure. The rings likely exhibit spiral density waves, shepherd moons, and other gravitational phenomena, familiar from Saturn's rings, but operating on a much grander scale. The massive ring system may also influence the planet's rotation and magnetic field through gravitational coupling. Orbital resonances play crucial roles in maintaining the structure of the ring system. The gravitational interactions between ring particles and embedded moons create resonant regions where particles accumulate or are excluded, leading to the observed gaps and density variations. These resonances help stabilize the ring structure over long timescales, despite the system's youth and dynamic nature. The parent star is a young, sun-like star with properties similar to our own sun, but at a much earlier stage of evolution. The star's youth corresponds to the early phases of planetary system formation, when massive circumplanetary disks and ring systems are more common. This system may represent a snapshot of how gas giant planets and their moon systems appeared during the early stages of our own solar system's formation. Atmospheric interactions between the planet and its ring system create additional complexity in the system's evolution. The magnetic field, if present, would interact with charged particles in the rings, potentially driving ring particle dynamics and creating aurora phenomena in the planet's upper atmosphere. These magnetospheric interactions could influence both atmospheric chemistry and ring evolution. The long-term evolution of the ring system likely involves the gradual accretion of ring material into larger moons. Computer simulations suggest that the massive ring system is gravitationally unstable and will eventually collapse to form a system of large moons orbiting the planet. This process may already be underway. As evidenced by the gaps in the ring system, that suggests the presence of forming moons. Tidal forces within the ring system create additional evolutionary pressures that shape the distribution and dynamics of ring material. The enormous extent of the ring system means that different regions experience varying tidal forces from the central planet, leading to differential evolution and the formation of distinct ring regions with different characteristics and dynamics. The detection methods used to study the ring system demonstrate the power of transit photometry in revealing the architecture of distant planetary systems. The detailed light curve obtained during the ring system's transit provides information about ring opacity, gap widths, and particle distributions that would be impossible to obtain through direct imaging with current technology. Comparative studies between this ring giant and other ring-bearing objects help astronomers understand the factors that control ring system formation and evolution. The extreme properties of this ring system place it at one end of the spectrum of known ring systems, providing insights into the physical processes that govern circumplanetary disk evolution under extreme conditions. Future observations of the system may reveal additional transits as the planet's orbital period brings the ring system back between the star and Earth. However, the planet's estimated orbital period of 10 to 20 years means that opportunities for detailed study are relatively rare, making each potential transit event extremely valuable for advancing our understanding of this remarkable system. The magnetic field structure would be dramatically influenced by the presence of such a massive ring system. The interaction between planetary magnetic fields and ring particles creates complex current systems that could generate their own magnetic field contributions. These interactions might produce spectacular aurora displays and radio emissions detectable from Earth. The existence of this object challenges our understanding of ring system stability and formation mechanisms. Traditional models suggest that such extensive ring systems should be gravitationally unstable and collapse rapidly into moon systems. The apparent stability over millions of years indicates that our understanding of ring dynamics may need significant revision. The study of this ring giant provides valuable insights into the early stages of moon system formation around gas giant planets. The ring system may represent a transitional phase between the initial circumplanetary disk and the final moon system, offering a unique window into processes that occurred in our own solar system billions of years ago, but are no longer directly observable. Carot 7b, the lava ocean planet. In the constellation Monoceros, approximately 489 light-years from Earth, exists a world where the very ground beneath would flow like water, and the sky rains liquid rock. This super-Earth represents one of the most extreme terrestrial planets ever discovered, a place where surface temperatures reach 2,000 degrees Celsius, and molten silicate oceans cover vast regions of the dayside. This hellish world challenges our understanding of rocky planet formation and demonstrates the incredible diversity of terrestrial environments that can exist in the universe. This planet orbits incredibly close to its parent star, completing one full revolution in just 20.4 hours, while maintaining a distance of only 2.6 million kilometers from its stellar companion. This proximity places it well within the orbit that Mercury maintains around our Sun, subjecting the surface to intense stellar radiation that fundamentally transforms the planet's composition and atmospheric dynamics. Classified as a super-Earth, this world contains approximately 4.8 times the mass of our home planet and possesses a radius about 1.7 times larger than Earth's. Despite its increased size, it maintains a density similar to Earth's, indicating that it consists primarily of rocky materials rather than the gaseous compositions found in larger planets. This rocky composition becomes crucial in understanding the extreme surface conditions that characterize this world. Tidal locking plays a fundamental role in shaping the extreme environment. The close orbit has synchronized the planet's rotation period with its orbital period, meaning one hemisphere permanently faces the star, while the other remains in eternal darkness. This configuration creates one of the most dramatic temperature contrasts found anywhere in the known universe, with dayside temperatures reaching 2,000 degrees Celsius, while the night side may cool to several hundred degrees below zero. The dayside presents a landscape unlike anything found in our solar system. The extreme temperatures are sufficient to melt most silicate minerals, creating vast oceans of liquid rock that span entire continents. These lava seas likely consist of molten basalt, granite, and other common rocky materials that exist as flowing liquids under the intense stellar heating. The surface would glow with its own thermal radiation, creating a world that literally glows red hot across its entire day side. Atmospheric conditions are equally extreme and fundamentally different from those found on planets in our solar system. The intense surface heating vaporizes rock materials, creating an atmosphere composed of silicate vapor, sodium, potassium, and other heavy elements typically found in solid form. This rock vapor atmosphere creates a hellish environment where the very air consists of vaporized stone and metal compounds. Atmospheric dynamics are driven by the extreme temperature gradient between the day and night sides. Powerful circulation patterns transport heat from the molten day side toward the frozen night side, creating atmospheric winds that may reach supersonic speeds. These circulation patterns also redistribute the rock vapor atmosphere, potentially creating weather systems where liquid rock condenses and falls as precipitation on the cooler night side. The formation history likely involves significant atmospheric evolution and mass loss over geological timescales. The planet may have originally possessed a substantial atmosphere similar to Venus, but the intense stellar radiation and proximity to its star gradually stripped away lighter atmospheric components, leaving behind the current rock vapor envelope. This evolutionary process demonstrates how close-orbiting planets can be transformed by stellar interactions. Volcanic activity, if present, would operate under completely different conditions than volcanic processes on Earth. With surface temperatures already exceeding the melting points of most silicate materials, traditional volcanism becomes meaningless. Instead, the planet may experience a form of global volcanism where the entire day side exists in a perpetual state of melting and solidification, driven by atmospheric circulation and tidal heating. The magnetic field faces unique challenges due to the extreme thermal environment. The molten surface conditions might affect the planet's ability to maintain a strong magnetic field, as the extreme temperatures could disrupt the convective processes in the core that typically generate planetary magnetic fields. However, the substantial mass suggests it might still possess a partially molten core, capable of magnetic field generation. Tidal heating contributes additional energy to the already extreme thermal budget. The planet's proximity to its star subjects it to powerful tidal forces that continuously deform its shape as it orbits. This tidal flexing generates internal heat through friction, supplementing the intense stellar heating and potentially contributing to the global molten state. The atmospheric escape rate represents an ongoing evolutionary process that continues to shape the planet's properties. The combination of high temperatures and intense stellar radiation drives continuous atmospheric loss, particularly of lighter elements. The planet likely loses substantial amounts of its rock vapor atmosphere to space, requiring continuous replenishment through surface evaporation to maintain atmospheric pressure. Chemical differentiation processes operate under extreme conditions that may create unique geological structures. The perpetual melting and solidification cycles, driven by atmospheric circulation, could lead to chemical separation of different rock types, potentially creating regions enriched in specific minerals or elements. These processes might generate geological patterns, unlike anything found on planets with solid surfaces. The night side presents an equally fascinating but contrasting environment. While still extremely hot by Earth standards, the lack of direct stellar heating allows for some cooling and potentially the formation of solidified rock surfaces. The boundary region between day and night sides, known as the terminator, likely experiences the most dynamic conditions as atmospheric circulation transports heat and rock vapor between the two extremes. Observational studies have provided detailed measurements of the thermal emission and atmospheric properties. Space-based infrared telescopes can detect the intense heat radiation from the day side, confirming the extreme surface temperatures and providing insights into atmospheric composition. These observations represent some of the most detailed thermal measurements ever obtained for a rocky exoplanet. The parent star is a G-type star similar to our Sun, but slightly less massive and luminous. Despite the star's relatively modest properties, the extreme proximity creates the intense radiation environment responsible for the hellish conditions. This demonstrates how orbital distance, rather than stellar properties alone, determines planetary surface conditions. Comparative studies with other super-Earths help astronomers understand the factors that control rocky planet evolution under extreme conditions. This world serves as a natural laboratory for studying rock physics, atmospheric chemistry, and planetary thermal processes under conditions impossible to replicate in terrestrial laboratories. Future observations may reveal additional details about atmospheric composition and surface properties. Advanced spectroscopic techniques could detect specific rock vapor species in the atmosphere, providing insights into geological composition and the processes that govern surface-atmosphere interactions on this extreme world. The existence of this lava ocean planet expands our understanding of terrestrial planet diversity and demonstrates that rocky worlds can exist under conditions far more extreme than previously imagined. This planet serves as a reminder that the universe contains environments that challenge our preconceptions about planetary habitability and the limits of rocky planet survival in close stellar orbits. Kepler 438b, Earth-like but constantly irradiated. In the constellation Lyra, approximately 470 light-years from Earth, exists a world that represents both the promise and peril of exoplanet discovery. This planet possesses many characteristics that make it remarkably similar to our home planet, earning it recognition as one of the most Earth-like worlds ever discovered. Yet this tantalizing similarity masks a deadly reality. The planet orbits a violently active red dwarf star that bombards its surface with lethal radiation, transforming what might have been a haven for life into a constantly sterilized wasteland. The planet completes one orbit around its parent star every 35.2 Earth days, maintaining a distance that places it squarely within the habitable zone where liquid water could theoretically exist on its surface. It receives approximately 40% more energy from its star than Earth receives from the Sun, creating surface temperatures that could support liquid water under the right atmospheric conditions. This energy input falls within the range considered potentially suitable for maintaining temperate climates. This world exhibits remarkable similarities to Earth in terms of size and composition. With a radius only 12% larger than Earth's, it falls into the category of potentially rocky planets that could possess solid surfaces similar to terrestrial worlds. Its estimated mass suggests a composition dominated by silicate rocks and metals, creating a planet that might feature continents, oceans, and geological processes familiar from our own planet. However, the parent star presents conditions that fundamentally undermine the planet's potential habitability. This red dwarf star, while smaller and cooler than our Sun, exhibits extreme magnetic activity that generates powerful stellar flares on a regular basis. These flares release enormous amounts of high-energy radiation, including deadly ultraviolet light and X-rays that would sterilize any life forms on the planet's surface. Stellar flare events occur with alarming frequency, with major flares erupting approximately every few hundred days. During these events, the star's brightness can increase by several times its normal output in the high-energy portions of the electromagnetic spectrum. The intensity of these flares far exceeds anything experienced in our solar system, where even the most powerful solar flares pale in comparison to the routine stellar activity of this host star. The radiation environment around this exoplanet creates conditions hostile to life as we know it. The constant bombardment of high-energy particles and electromagnetic radiation would break down complex organic molecules, damage DNA, and prevent the formation of the protective ozone layers that shield life on Earth. Any atmosphere the planet might possess would face continuous erosion from the stellar wind and radiation pressure. Atmospheric modeling reveals the challenges faced by any potential atmosphere in this harsh radiation environment. The intense stellar activity would continuously strip away atmospheric gases, particularly lighter elements like hydrogen and helium. Even heavier atmospheric components like nitrogen and carbon dioxide might struggle to persist over geological timescales under such intense radiation bombardment. The magnetic field, if present, would play a crucial role in determining the planet's ability to retain an atmosphere and protect its surface from stellar radiation. A strong planetary magnetic field could deflect some of the charged particles from stellar flares, creating a protective magnetosphere similar to Earth's. However, the intensity of radiation from the host star might overwhelm even the strongest planetary magnetic field. Tidal locking likely affects the planet due to its close orbit around its parent star. This means one hemisphere permanently faces the star, while the other remains in darkness, creating extreme temperature variations across the surface. The day side would bear the full brunt of stellar radiation and flare activity, while the night side might offer some protection from the most intense radiation events. The surface conditions would vary dramatically, depending on the atmospheric properties and magnetic field strength. In the absence of a substantial atmosphere or magnetic protection, the surface would experience radiation levels thousands of times higher than those that would be lethal to Earth-based life forms. Even microbial life forms, known for their resilience to extreme conditions, would struggle to survive such intense radiation exposure. Water, if present, would face continuous threats from the stellar radiation environment. The high-energy radiation would break apart water molecules through photodissociation, gradually depleting any surface water reservoirs. The lack of a protective ozone layer would allow ultraviolet radiation to penetrate deeply into any oceans or lakes, preventing the formation of the chemical gradients necessary for life. The geological evolution might differ significantly from Earth due to the effects of intense stellar radiation on surface and atmospheric processes. The continuous energy input from stellar flares could drive unique chemical reactions in surface rocks and alter the planet's geological cycles. These processes might create mineral formations and surface features unlike anything found on planets orbiting more stable stars. Climate dynamics would be dominated by the variable energy output from the flare-active star. The planet's climate system would need to respond continuously to dramatic changes in stellar radiation, creating weather patterns and atmospheric circulation systems unlike those found on planets orbiting stable stars. These variable conditions would make it extremely difficult for complex ecosystems to establish and persist. The discovery highlights the challenges inherent in assessing exoplanet habitability, based solely on orbital characteristics and planetary properties. While the planet's size, orbital distance, and estimated temperature initially suggested Earth-like conditions, detailed study of the stellar environment revealed conditions hostile to life. This serves as a crucial reminder that stellar properties play an equally important role in determining habitability. Red dwarf stars like this one represent the most common type of star in our galaxy, making up approximately 75% of all stellar objects. The hostile radiation environment around this planet raises important questions about the habitability of planets orbiting red dwarf stars in general. If such radiation environments are typical, it could significantly reduce the number of potentially habitable worlds in our galaxy. The atmospheric escape processes provide insights into how stellar activity affects planetary evolution over long timescales. The continuous loss of atmospheric gases due to stellar radiation represents an ongoing evolutionary process that gradually transforms planetary environments. Understanding these processes helps astronomers predict the long-term fate of planets orbiting active stars. Comparative studies between this planet and those orbiting more stable stars help scientists understand the factors that promote or inhibit habitability in different stellar environments. The contrast between Earth-like physical properties and a hostile radiation environment illustrates the complex interplay of factors that determine whether a world can support life. Future observations may reveal additional details about atmospheric properties and surface conditions. Advanced spectroscopic techniques could detect atmospheric constituents or surface minerals that provide insights into how the planet responds to its harsh stellar environment. These studies would enhance our understanding of planetary evolution in high radiation environments. The existence of this radiation-bathed world serves as a sobering reminder that the search for habitable planets requires careful consideration of all environmental factors, not just the basic orbital and physical characteristics that initially suggest Earth-like conditions. This planet demonstrates that the universe contains many worlds that appear promising at first glance, but harbor conditions that would challenge even the most resilient forms of life. OGL 2016 BLG 1928 the starless planet. In the depths of interstellar space, drifting alone through the cosmic void without the warmth of a parent star, exists one of the most haunting and mysterious objects ever discovered. This rogue planet represents a world that has been cast out from its original solar system to wander eternally through the darkness between the stars. This solitary wanderer challenges our understanding of planetary formation and evolution, while offering a glimpse into the violent processes that can tear apart entire planetary systems. The discovery came through gravitational microlensing, a technique that detects objects by observing how their gravity bends and magnifies the light from background stars. When this rogue body passed directly between Earth and a distant star, its gravitational field acted as a cosmic lens, briefly brightening the background star in a characteristic pattern that revealed the presence of the intervening object. This fleeting gravitational signature lasted only a few days, providing astronomers with a rare opportunity to study this elusive class of objects. The planet's mass is estimated to be similar to Earth's, making it one of the smaller rogue planets detected to date. Most previously discovered rogue planets have been massive gas giants, but this one represents a terrestrial world that once might have possessed rocky surfaces, atmospheres, and potentially even conditions suitable for life before its violent ejection from its original solar system. Its Earth-like mass suggests it formed through similar accretion processes that created the terrestrial planets in our own solar system. The journey from its original solar system into interstellar space likely involved dramatic gravitational interactions with other massive objects. Computer simulations suggest that rogue planets typically form through close encounters with gas giant planets or stellar companions that provide the gravitational kicks necessary to exceed the escape velocity of their parent star. These violent ejection events represent some of the most catastrophic processes that can occur during planetary system evolution. Without the heating provided by a nearby star, this world exists in conditions of perpetual cold that would make Antarctica seem tropical by comparison. Surface temperatures on the rogue planet likely hover around -200 degrees Celsius or lower, cold enough to freeze atmospheric gases like nitrogen and oxygen into solid form. Any water that might have existed on the planet's surface would have frozen solid within a few million years of ejection from its parent system. The atmosphere, if it still possesses one, would differ dramatically from atmospheric envelopes around planets in stable solar systems. Without stellar heating to drive atmospheric circulation and weather patterns, any remaining gases would gradually settle into a thin, static layer, or potentially freeze out entirely onto the planet's surface. The loss of atmospheric dynamics would fundamentally alter chemical processes and eliminate the complex interactions between surface and atmosphere that characterize planets in normal solar systems. Internal heat sources become crucial for understanding the long-term evolution of a world like this. Radioactive decay of elements like uranium, thorium, and potassium within the planet's interior continues to generate heat even in the absence of stellar radiation. This internal heating might maintain subsurface liquid water reservoirs beneath kilometers of ice, creating potential habitats for extremophile organisms that could survive in the planet's deep interior. The magnetic field, if it persists, could still operate long after the planet's ejection from its original solar system, provided a molten core remains active via radioactive heating. A planetary magnetic field would offer some protection against cosmic radiation and charged particles from interstellar space, though the overall radiation environment in deep space differs significantly from the stellar wind environments experienced by planets in conventional systems. Geological processes would operate under unique conditions not found on planets orbiting stars. Without tidal heating from a nearby star or the thermal cycling caused by day-night temperature variations, geological activity would depend entirely on internal heat sources. Volcanic activity, if present, might create isolated warm zones on an otherwise frozen world, potentially supporting localized environments with liquid water. The search for rogue planets represents one of the most challenging areas of exoplanet research, as these worlds emit virtually no light and can only be detected through indirect methods like gravitational microlensing. The brief detection events that reveal rogue planets provide limited information about their properties. making objects like this one tantalizing mysteries that may never be studied in detail with current technology. Population studies suggest that rogue planets may be surprisingly common throughout our galaxy, with some estimates indicating that they could outnumber stars by significant factors. If these estimates are correct, the Milky Way might contain billions or even trillions of rogue planets drifting through interstellar space, representing a vast population of hidden worlds that remain largely invisible to current detection methods. The ejection mechanisms that create rogue planets provide insights into the dynamical evolution of planetary systems. The gravitational interactions that can eject planets from their parent systems also reshape the architecture of the remaining planets, potentially explaining some of the unusual orbital configurations observed in exoplanetary systems. Understanding these processes helps astronomers predict the long-term stability of planetary systems. Chemical evolution on this wandering body would proceed along pathways completely different from planets that remain in stellar systems. Without stellar ultraviolet radiation to drive photochemical reactions, chemical processes would depend on cosmic ray interactions, radioactive decay, and potentially geothermal activity. These alternative energy sources might support unique chemical environments not found elsewhere in the universe. The possibility of life surviving on such a planet depends critically on the availability of liquid water and energy sources. While surface conditions would be hostile to most known forms of life, subsurface environments heated by radioactive decay or residual internal heat might maintain liquid water reservoirs. These hidden oceans could potentially support ecosystems based on chemosynthetic organisms that derive energy from chemical reactions rather than sunlight. Tidal heating from large moons, if any are present, could provide additional energy sources that extend the habitability potential of this rogue system. The gravitational interactions between a planet and its moons continue to operate even in interstellar space, potentially maintaining geological activity and subsurface liquid water for billions of years after ejection from the original stellar system. The detection of this rogue world demonstrates the power of large-scale astronomical surveys to discover rare and unusual objects that would otherwise remain hidden. The optical gravitational lensing experiment that led to this discovery monitors millions of stars simultaneously, looking for the brief gravitational lensing events that reveal the presence of otherwise invisible objects like rogue planets. Future space-based telescopes with improved sensitivity might eventually enable direct imaging of nearby rogue planets, potentially revealing surface features, atmospheric properties, and other characteristics that remain hidden with current detection methods. Such observations would provide unprecedented insights into the properties and evolution of these mysterious wandering worlds. The existence of a starless planet like this one expands our conception of planetary environments and demonstrates that worlds can exist and potentially evolve in complete isolation from stellar systems. These cosmic wanderers serve as natural laboratories for studying planetary physics under extreme conditions and remind us that the universe contains environments and evolutionary pathways that we are only beginning to understand. Kepler 22b, the Great Unknown. In the constellation the Cygnus, approximately 620 light-years from Earth, lies a world that once sparked global excitement as a potential second Earth. With its position in the habitable zone and a size only modestly larger than our own planet, this exoplanet captured imaginations and headlines alike. Yet, despite the initial optimism, this mysterious world remains frustratingly elusive, representing the tantalizing gap between what we hope to find in the universe and what we are currently able to confirm. This planet orbits a G-type star similar to our Sun, completing a full revolution every 289 Earth days. Its orbital distance of approximately 112 million kilometers places it comfortably within the star's habitable zone, the region where temperatures could, in theory, support liquid water on a planetary surface. This position makes it a prime candidate in the search for potentially habitable exoplanets. With a radius about 2.4 times that of Earth, the planet falls into the category of super-Earths or mini-Neptunes, depending on its composition. Its size suggests two possible outcomes. It could be a rocky world with a thick atmosphere, similar in structure to Earth but scaled up. Or it might be a small gas planet with no solid surface, more like Neptune in miniature. Without additional data, its true nature remains one of the most pressing questions surrounding the planet. The surface conditions depend almost entirely on atmospheric composition, which remains undetermined. If the planet possesses a thick atmosphere rich in greenhouse gases, surface temperatures could rise significantly, potentially creating a runaway greenhouse effect, similar to Venus. Alternatively, a thin atmosphere could allow for Earth-like climates, especially if the planet rotates in a way that promotes even heat distribution. The lack of confirmed mass measurements presents a major obstacle to understanding the planet's internal structure. Mass determines density, which in turn reveals whether the planet is primarily rocky or gaseous. Without this information, scientists can only speculate about surface conditions, atmospheric retention, and the likelihood of oceans, continents, or cloud layers. The host star provides stable, sun-like energy, creating a relatively calm radiation environment that would support atmospheric stability if the planet possesses a magnetic field. The star's similarity to our Sun adds to the appeal, as it suggests the planet's climate might resemble Earth's, assuming all other variables align. Tidal locking is unlikely due to the planet's relatively distant orbit. This increases the probability that the planet experiences a regular day-night cycle, distributing stellar energy more evenly and reducing the likelihood of extreme temperature differences between hemispheres. Such rotation would enhance habitability potential and promote climate stability if other conditions permit. The discovery came through NASA's Kepler Space Telescope, which observed the planet's transit across the face of its host star. This method revealed its size and orbital period, but left many other details unresolved. Follow-up observations with more advanced telescopes are needed to determine atmospheric composition, surface temperature, and potential biosignatures. The search for Earth-like worlds focuses heavily on identifying planets in the habitable zone. But, as this case demonstrates, location alone does not determine habitability. A planet can exist in the Goldilocks zone and still be completely uninhabitable due to factors such as atmospheric composition, geological activity, or magnetic field strength. Kepler 22. B embodies this paradox, sitting on the edge of promise and mystery. Atmospheric modeling provides hypothetical scenarios based on assumptions about composition and structure. If the planet has a thick atmosphere composed of nitrogen and carbon dioxide, with trace amounts of water vapor, it might support surface water. Alternatively, an atmosphere dominated by hydrogen or helium would indicate a gas-dominated mini-Neptune with no solid surface. Cloud cover, if present, could influence surface temperatures significantly by reflecting stellar radiation. A highly reflective atmosphere would lower surface temperatures, while thick clouds could trap heat and elevate temperatures well above the freezing point of water. These opposing effects create wide uncertainty in climate predictions. The possibility of oceans remains one of the most intriguing aspects. A planet of this size could retain large quantities of water, potentially forming deep global oceans. These so-called water worlds could possess conditions favorable to microbial life, even if lacking continents or dry land. Alternatively, the planet might be covered in thick ice or be entirely dry and barren. Magnetic field generation depends on internal structure, particularly the presence of a molten metallic core. If the planet is rocky with a core similar to Earth's, it might produce a protective magnetic field that shields the surface from cosmic radiation and preserves atmospheric gases. If gaseous or lacking internal dynamo action, it might be completely exposed to space weather effects. The evolution of the planet's atmosphere is critical to its current state. In the early stages of planetary formation, high-energy stellar radiation can strip away atmospheres, especially for planets lacking magnetic fields. Over time, volcanic outgassing or cometary impacts might replenish lost gases. The current atmospheric balance reflects this history, but remains unknown without direct observation. The habitability potential also depends on geologic activity. Plate tectonics, volcanic eruptions, and carbon cycling contribute to climate regulation on Earth. If this exoplanet possesses active geology, it might support similar climate stabilization mechanisms. A geologically dead world, on the other hand, would experience climate extremes and a static, potentially toxic atmosphere. Surface gravity, estimated to be stronger than Earth's due to the planet's size, would influence everything from atmospheric pressure to potential plant and animal physiology if life exists. Higher gravity would make the atmosphere denser, enhancing greenhouse effects, and possibly affecting the types of weather systems that develop. The planet's age also plays a role in its potential to support life. If the system is young, conditions may still be unstable, with frequent asteroid impacts and high stellar radiation. A mature system increases the likelihood of climate stability and biological evolution. The host star's characteristics suggest a system old enough to allow life to develop, assuming other conditions are met. Comparative studies with other super-Earths in habitable zones help refine models of planetary evolution and habitability. Kepler provides a key data point in this effort, serving as both a target for future research and a benchmark for evaluating similar discoveries. Technological advancements in space telescopes may one day provide direct imaging or spectroscopic analysis of the atmosphere, revealing gases like oxygen, methane, or water vapor that could suggest biological activity. Until then, the planet remains an enigmatic symbol of what we hope to find among the stars, a second Earth waiting to be understood. This world stands at the frontier of scientific discovery, not because it confirms the existence of habitable exoplanets, but because it highlights the limitations of our current knowledge and the vast potential that lies beyond. It's not yet Earth 2.0, but it is a reminder that such a world may be just around the corner. GJ 504, the Pink Giant. In the constellation Virgo, approximately 57 light-years from Earth, orbits one of the most visually striking and scientifically puzzling worlds ever discovered. This pink giant stands out not merely for its massive size or distant orbit, but for a characteristic that challenges our understanding of planetary atmospheres and formation processes. This extraordinary world glows with a distinctive pink hue, earning it recognition as one of the most unusual gas giants in our cosmic neighborhood. The planet's remarkable coloration stems from complex atmospheric chemistry operating under extreme conditions. Unlike the familiar blues and browns of gas giants in our solar system, this object radiates in wavelengths that create its signature magenta appearance. This unusual color results from the world's youth and internal heat, combined with atmospheric components that absorb and emit light in ways that produce this extraordinary visual signature. This distant gas giant maintains an orbital distance of approximately 44 astronomical units from its parent star, placing it farther from its sun than Neptune orbits from ours. This distant location contributes to its unique properties and helps preserve the atmospheric conditions responsible for its distinctive appearance. The remote orbit also suggests formation mechanisms that differ significantly from the gas giants we observe in our own solar system. Its mass presents intriguing questions about planetary formation and evolution. With a mass approximately 4 times greater than Jupiter's, this object occupies a transitional zone between massive planets and brown dwarf stars. This intermediate size places it in a category of objects that blur the traditional boundaries between planets and failed stars, offering insights into the diverse outcomes of stellar and planetary formation processes. Temperature measurements reveal that this young world maintains a surface temperature of approximately 240 degrees Celsius, making it one of the coolest directly imaged exoplanets known to science. This relatively moderate temperature, combined with significant internal heat generation, creates atmospheric conditions that allow complex chemical processes to operate and maintain the planet's distinctive coloration over astronomical timescales. The pink coloration likely results from specific molecular compounds in the atmosphere that absorb blue and green wavelengths, while allowing red and infrared radiation to escape. Scientists theorize that alkali metals, complex hydrocarbons, or exotic atmospheric chemistry unique to young, massive planets might contribute to this remarkable optical property. The exact mechanisms remain subjects of ongoing research and debate. Atmospheric composition studies suggest that this planet possesses a hydrogen and helium-dominated atmosphere, similar to other gas giants, but with trace components that create its unique spectral signature. Water vapor, methane, and carbon monoxide have been detected in the atmosphere, along with other molecular species that contribute to its complexity, optical properties, and thermal characteristics. Its formation history presents puzzles that challenge conventional theories of gas giant development. Located too far from its parent star for traditional core accretion models to explain its formation, this gas giant likely formed through gravitational instability processes or migration from closer orbital positions. These formation scenarios would influence its atmospheric composition and explain its unusual properties. Cloud formation processes here operate under conditions dramatically different from those found in our solar system. The atmospheric pressure, temperature gradients, and chemical composition create environments where exotic cloud types might form from materials rarely encountered in terrestrial meteorology. These cloud systems could contribute to the object's optical properties and thermal regulation. The parent star resembles our Sun, but appears slightly more massive and luminous. This G-type star provides the external energy that interacts with internal heat sources to maintain atmospheric circulation patterns and chemical processes. The stellar radiation influences atmospheric chemistry and helps drive the complex processes responsible for this world's distinctive appearance. Magnetic field properties likely differ significantly from those of solar system gas giants due to the unique mass, composition, and thermal characteristics. The magnetic field generation mechanisms, if they exist, would influence atmospheric retention, radiation interaction, and the overall evolution of its distinctive atmospheric properties over cosmic time scales. Seasonal variations, if they occur, would follow patterns determined by the planet's orbital characteristics and axial orientation. The distant orbit results in extremely long seasonal cycles, with each season lasting decades or centuries. The nature of these extended seasons and their effects on atmospheric dynamics remain largely theoretical. The direct imaging techniques used to study this object represent significant advances in exoplanet detection and characterization technology. The separation from its parent star and distinctive infrared emission make it an ideal target for direct observation methods that bypass the limitations of transit and radial velocity. Detection techniques used for most exoplanet discoveries. Atmospheric modeling efforts must account for the complex interplay between internal heat generation, stellar radiation, atmospheric chemistry, and circulation patterns. These models attempt to explain the observed properties while predicting characteristics that remain beyond current observational capabilities, including detailed atmospheric structure and dynamics. The estimated age of approximately 160 million years places this world in the category of young planetary systems, where formation processes remain active and evolutionary changes occur on relatively rapid timescales. This youth contributes to its high internal temperature and may explain the distinctive atmospheric properties and coloration mechanisms. Comparative studies between this world and other directly imaged exoplanets reveal the tremendous diversity that exists among gas giant worlds. Each directly imaged planet displays unique characteristics that reflect different formation histories, atmospheric compositions, and evolutionary pathways, highlighting the complexity of planetary system development throughout the galaxy. The study of this pink giant provides valuable insights into atmospheric physics under extreme conditions and helps refine our understanding of gas giant formation and evolution processes. This alien world serves as a natural laboratory for testing theories about planetary atmospheres, formation mechanisms, and the factors that determine planetary characteristics. Spectroscopic observations continue to reveal new details about the atmosphere and structure. Advanced instruments capable of analyzing the light spectrum provide information about molecular abundances, temperature profiles, and atmospheric dynamics that help explain its remarkable properties and distinctive appearance. The ongoing study of this unusual world represents part of humanity's broader effort to understand the incredible diversity of worlds that exist throughout our galaxy. Each planet like this expands our knowledge of planetary science and challenges our assumptions about the types of worlds that can form around other stars. Future observations using next-generation telescopes and advanced instrumentation may reveal additional details about the atmospheric composition, internal structure, and evolutionary history. These studies will help astronomers better understand the formation and evolution of gas giant planets and the factors that create such remarkable diversity among exoplanets. This pink giant continues to capture scientific attention as one of the most visually distinctive and scientifically valuable directly imaged exoplanets. Its unique properties provide ongoing opportunities for advancing our understanding of planetary atmospheres, formation as processes, and the remarkable variety of worlds that populate our cosmic neighborhood. TOI 849b, the naked planetary core. In the constellation Pictor, approximately 730 light-years from Earth, orbits one of the most extraordinary remnants of planetary evolution ever discovered. This stripped world represents what astronomers believe to be the exposed core of a former gas giant, a planet stripped of its atmospheric envelope through processes so violent and complete that only the dense, rocky heart of the original body remains. This remarkable object provides unprecedented insights into planetary formation, atmospheric loss, and the extreme environments that can reshape entire worlds. The planet completes one orbit around its parent star every 18.4 hours, placing it in an extremely close orbit that subjects it to intense stellar radiation and gravitational forces. This proximity exposes the core to surface temperatures exceeding 1,800 degrees Celsius, creating conditions hostile to any substantial atmosphere, and likely contributing to the complete loss of the gaseous envelope that once surrounded it. This remnant possesses a radius approximately 3.4 times larger than Earth's, yet maintains a density that suggests a composition dominated by rock and metal, rather than the lighter materials typically associated with planets of this size. This unusual combination of large radius and high density supports the theory that astronomers are observing the naked core of what was once a much larger gas giant planet. The mass of this object, estimated at approximately 40 times that of Earth, places it firmly in the realm of planetary cores rather than intact gas giant planets. This substantial mass, concentrated in a relatively compact volume, creates surface gravity conditions approximately 10 times stronger than those experienced on Earth, contributing to the planet's ability to retain its solid structure despite the extreme environmental conditions. Atmospheric stripping processes likely removed the original gaseous envelope through a combination of stellar radiation, stellar winds, and possibly interactions with other objects in the planetary system. The intense ultraviolet radiation from the nearby star would have heated the upper atmosphere to temperatures that allowed hydrogen and helium to escape to space, gradually eroding the entire atmospheric envelope over millions or billions of years. The composition of this exposed core likely consists of silicate rocks, iron, and other heavy elements that formed the solid foundation of the original gas giant. These materials, compressed under the immense pressures that existed within the original planet's interior, now form the surface and bulk composition of this unusual world. The core materials provide direct evidence of the building blocks used in gas giant formation. Thermal evolution models suggest that this planetary remnant continues to radiate heat generated during its formation and subsequent atmospheric loss processes. The interior likely maintains elevated temperatures due to residual heat from gravitational compression, radioactive decay of heavy elements, and possibly ongoing structural adjustments as the exposed body adapts to its new configuration without the insulating atmosphere. Surface conditions on this world present an environment unlike anything found in our solar system. The combination of extreme temperatures, intense stellar radiation, and the absence of atmospheric protection creates a world where rock surfaces might exist in partially molten states. Volcanic activity, if it occurs, would operate under conditions dramatically different from terrestrial volcanism. The discovery of this exposed core challenges traditional models of planetary system architecture and evolution. Most theoretical frameworks predict that planets forming so close to their stars should either be small, rocky worlds, or should migrate outward to cooler regions where they can retain substantial atmospheres. The existence of a stripped gas giant core in such an extreme orbit suggests more complex evolutionary pathways than previously considered. Tidal forces from the nearby star likely influence the internal structure and surface geology of this object. The extreme gravitational gradient across its diameter could drive ongoing geological activity and contribute to heat generation within the core. These tidal effects might also influence rotational characteristics and contribute to thermal evolution. Magnetic field generation depends on the internal structure and the presence of electrically conductive materials in the core. If this object retains a molten metallic interior, it might generate magnetic fields through dynamo processes similar to those operating in terrestrial planets. However, the extreme environmental conditions could alter these processes in unpredictable ways. The formation history of this planetary remnant likely involved initial development as a conventional gas giant in the outer regions of its planetary system, followed by inward migration and subsequent atmospheric loss. Alternative scenarios include formation closer to the star with immediate atmospheric stripping, or catastrophic events that removed the gaseous envelope through impacts or stellar interactions. Comparative studies with other unusual exoplanets help place this world in context within the broader population of planetary remnants and evolved bodies. It represents one extreme outcome of planetary evolution, demonstrating the dramatic changes that can occur when worlds experience severe environmental stress over astronomical timescales. Spectroscopic observations focus on detecting any remnant atmosphere or surface composition signatures that might provide additional evidence for its origin as a stripped gas giant core. These observations must overcome the challenges of studying a small, distant object that emits primarily thermal radiation rather than reflected starlight. Its location in what astronomers call the Neptunian desert makes this exposed core particularly significant for understanding planetary evolution. This region close to stars typically lacks planets of Neptune-like size, possibly because atmospheric stripping processes remove gaseous envelopes from planets that venture too close to their stars, leaving behind remnants like this. Climate modeling for this world focuses on understanding heat transport, surface temperature distribution, and the potential for maintaining any thin atmosphere despite the extreme stellar radiation. These models must account for the unique properties of an exposed planetary core and the absence of atmospheric insulation and circulation patterns. Seismic activity, if it occurs, would provide valuable information about the internal structure and composition of this object. The extreme tidal forces and thermal stresses acting upon it could drive geological processes that reshape the surface and provide insights into the core's physical properties and evolutionary history. The study of this stripped world contributes to broader understanding of planetary system dynamics and the factors that determine planetary survival in extreme environments. It serves as an example of how stellar radiation and gravitational forces can completely transform worlds over cosmic timescales, creating objects that challenge traditional planetary classification schemes. Future observations may reveal additional details about the surface composition, internal structure, and thermal properties of this remnant. These studies could provide direct observational evidence for theoretical models of gas giant core composition and help refine our understanding of planetary formation and evolution processes. The ongoing research surrounding this exposed core represents part of humanity's effort to understand the full range of planetary evolution outcomes and the extreme environments that can exist around other stars. This naked planetary core demonstrates the dynamic nature of planetary systems and the dramatic changes that can occur over billions of years of evolution. Technological advances in exoplanet characterization continue to provide new insights into unusual worlds like this. Each observation adds to our understanding of planetary physics, atmospheric loss processes, and the factors that determine whether planets can survive in extreme stellar environments. This stripped remnant stands as testament to the incredible diversity of outcomes possible in planetary evolution, representing a world that has survived the complete loss of its original atmosphere while maintaining its structural integrity. This remarkable object continues to provide unique insights into the fundamental processes that shape planetary systems throughout our galaxy. PSRB 1257 plus 12, ABC, planets around a dead star. In the constellation Virgo, approximately 2,300 light-years from Earth, 3 small worlds orbit one of the most extreme stellar remnants in our galaxy. These planets represent the first confirmed exoplanets ever discovered, Yet they exist in an environment so hostile and alien that they challenge our fundamental understanding of planetary formation and survival. These worlds circle a pulsar, the collapsed remnant of a massive star that ended its life in a catastrophic supernova explosion. The pulsar at the heart of this system represents what remains after a star at least 8 times more massive than our Sun exhausted its nuclear fuel and collapsed into an object only 20 kilometers in diameter. This neutron star contains more mass than our Sun, compressed into a sphere smaller than most cities, creating gravitational fields so intense that a teaspoon of its material would weigh as much as Mount Everest on Earth. The 3 planets maintain orbital periods of 25.3, 66.5, and 98.2 Earth days respectively, placing them at distances comparable to the inner regions of our solar system. The innermost world orbits closer to the pulsar than Mercury orbits our Sun, while the other 2 occupy positions that would place them between Mercury and Venus in our solar system. These close orbits subject all 3 bodies to radiation levels that would sterilize any known form of life. The discovery of these pulsar planets revolutionized astronomy by demonstrating that worlds could survive the violent death of their parent star and continue orbiting the resulting stellar remnant. The supernova explosion that created the pulsar would have released more energy in seconds than our Sun will produce over its entire 10 billion year lifetime. Yet somehow these objects endured this cosmic catastrophe and maintained stable orbits. Planetary masses reveal that all 3 are significantly smaller than Earth, with the innermost one possessing only 2% of Earth's mass, while the outer 2 contain approximately 4 and 3 times Earth's mass respectively. These relatively modest sizes suggest compositions dominated by rocky materials rather than the gaseous envelopes that characterize larger planets, though the extreme radiation environment makes traditional atmospheric retention impossible. The formation history of these bodies presents one of the most intriguing puzzles in planetary science. Scientists propose several scenarios to explain their existence, including survival from the original stellar system, a formation from debris ejected during the supernova explosion, or accretion from material in a disk surrounding the newly formed pulsar. Each formation mechanism would result in different compositions and characteristics. Radiation from the neutron star creates an environment utterly unlike anything experienced by planets in normal stellar systems. The collapsed star emits intense beams of electromagnetic radiation that sweep across space as it rotates 30 times per second, creating lighthouse-like pulses that give pulsars their name. This radiation includes high-energy particles and electromagnetic fields that would strip away any substantial atmosphere. Surface conditions on these pulsar-bound worlds likely resemble the most extreme environments imaginable, with temperatures potentially reaching hundreds of degrees due to radiation heating, combined with the complete absence of protective atmospheres. These planets experience constant bombardment by high-energy particles that would prevent the formation of complex chemical compounds necessary for any conceivable form of life. Tidal forces from the neutron star's intense gravitational field likely keep each planet in synchronous rotation, with one hemisphere permanently facing the pulsar while the other remains in perpetual darkness. This configuration would create extreme temperature gradients across their surfaces, with the day side experiencing intense radiations heating, while the night side radiates heat into the cosmic background. The absence of stellar wind, as conventionally understood, around the pulsar creates unique conditions for orbital dynamics. Instead of the steady stream of particles that normal stars emit, the neutron star produces highly collimated beams of radiation and charged particles that interact with these planets only when the rotating beams sweep across their positions during each 30-millisecond rotation period. Magnetic field interactions between the neutron star and these closely orbiting bodies likely influence orbital dynamics and surface conditions. The pulsar's magnetic field can be trillions of times stronger than Earth's, potentially driving electrical currents within the planets and contributing to heating of their interiors through electromagnetic induction. The precision required to detect these exoplanets demonstrates the remarkable regularity of pulsar timing. Astronomers discovered them by measuring tiny variations in the arrival times of radio pulses from the neutron star, detecting gravitational effects as small as a few microseconds, caused by the planet's orbital motions. This technique requires timing precision equivalent to detecting changes smaller than the width of a human hair at distances of kilometers. Atmospheric retention remains virtually impossible here due to the intense radiation environment and relatively small planetary masses. Any gases released from their surfaces through volcanic activity or impact events would be quickly ionized and stripped away by the pulsar's radiation, preventing the development of substantial atmospheric envelopes. The long-term stability of these orbits depends on complex interactions between gravitational forces, radiation pressure, and tidal effects. Computer simulations suggest that the system has remained dynamically stable for millions of years since its formation, indicating that even in such hostile environments, planetary systems can persist over geological timescales. The absence of water or other volatile compounds on these rocky worlds results from both the extreme radiation and the violent history of their formation or survival. Any water present during the supernova event would have been vaporized and lost to space, while subsequent formation from debris would have occurred under conditions too hot and energetic to allow volatile retention. The study of this trio contributes to our understanding of planetary system resilience and the extreme conditions under which worlds can form and survive. These planets represent natural laboratories for studying physics under conditions that cannot be replicated on Earth or in laboratory experiments. Future observations of pulsar planetary systems may reveal additional details about formation, mechanisms, survival strategies, and the range of environments where worlds can exist. Advanced timing techniques and new radio telescopes continue to improve our ability to detect and characterize such exotic planetary companions. The legacy of these three planets extends beyond their individual characteristics to their role in establishing the field of exoplanet science. As the first confirmed worlds beyond our solar system, they opened humanity's eyes to the incredible diversity of planetary systems and demonstrated that planets could exist in environments far more extreme than previously imagined. Theoretical models of planet formation around neutron stars continue to evolve as astronomers gather more observational data and refine their understanding of pulsar physics. These models help explain how such bodies can exist in extreme environments and predict the properties of similar systems throughout the galaxy. These worlds remain among the most extreme planets known to science, existing in an environment where the very definition of habitability loses all meaning. Their continued existence serves as a testament to the remarkable resilience of planetary systems and the incredible diversity of worlds that populate our universe. Kelt 9b, hotter than stars. In the constellation Cygnus, approximately 670 light-years from Earth, orbits one of the most extreme worlds ever discovered in our galaxy. This ultra-hot planet holds the distinction of being among the hottest known, with dayside temperatures exceeding 4,300 degrees Celsius. This extraordinary heat makes the surface hotter than many stars, creating conditions so extreme that the very concept of a planetary atmosphere takes on entirely new meaning in this alien environment. The planet completes one orbit around its massive, blue-white parent star every 1.48 Earth days, maintaining such close proximity that it experiences stellar radiation more intense than almost any other known world. This tight orbital configuration subjects the gas giant to gravitational forces and energy input that fundamentally alter its physical properties and atmospheric behavior, creating a world unlike anything found in our solar system. This object possesses a mass approximately 2.9 times that of Jupiter, yet maintains a significantly larger radius due to the extreme heating from its parent star. The intense stellar radiation causes the atmosphere to expand dramatically, creating a bloated world with a density lower than water. This thermal expansion demonstrates how extreme stellar heating can fundamentally alter planetary structure and composition. The parent star represents one of the hottest stars known to host a planet, with surface temperatures reaching approximately 10,170 degrees Celsius. This A-type star burns through its nuclear fuel at a rapid rate, producing intense ultraviolet radiation that bathes its companion in energy levels that would vaporize most known materials. The stellar mass, estimated at 2.5 times that of our Sun, creates gravitational and radiative environments far more extreme than those found in typical planetary systems. Atmospheric conditions on this world challenge traditional understanding of planetary meteorology and chemistry. The extreme temperatures cause hydrogen molecules to dissociate into individual atoms, while heavier elements that would normally form solid materials exist as vapors in the extended atmosphere. Water, carbon dioxide, and methane cannot exist in molecular form under these conditions, breaking apart into their constituent atoms almost immediately. The planet likely experiences extreme atmospheric escape, with material from its outer layers continuously streaming away into space due to the intense stellar heating. This mass loss process gradually reduces the atmospheric envelope over time, though the massive size of the object allows it to retain substantial material despite the ongoing escape processes. Tidal forces from the nearby star have locked this planet into synchronous rotation, with one hemisphere permanently facing the star, while the other remains in perpetual darkness. This configuration creates the most extreme temperature gradient known on any planet, with the day side reaching temperatures that rival stellar photospheres, while the night side might maintain temperatures several thousand degrees cooler. The day side atmosphere likely exists in a plasma state, with electrons stripped from their atomic nuclei due to the extreme temperatures and intense stellar radiation. This ionized atmosphere would behave more like stellar material than conventional planetary atmospheres, with electrical conductivity and magnetic field interactions playing dominant roles in atmospheric dynamics. Atmospheric circulation patterns on this planet operate under conditions where traditional meteorological concepts lose their applicability. The extreme temperature gradients between day and night sides would drive circulation velocities potentially reaching thousands of kilometers per hour, creating atmospheric dynamics more similar to stellar convection than planetary weather systems. The chemical composition of the atmosphere undergoes continuous transformation due to the extreme thermal environment. Elements that exist as refractory compounds under normal conditions vaporize and participate in gas phase chemistry, while lighter elements escape to space. This ongoing chemical evolution gradually alters the atmospheric properties and mass over astronomical timescales. Magnetic field generation likely differs dramatically from processes operating in cooler gas giants. The ionized atmospheric material could generate magnetic fields through magnetohydrodynamic processes, while interactions with the stellar magnetic field create complex electromagnetic environments that influence atmospheric retention and circulation patterns. Observational studies of this hot giant have detected various atomic species in its extended atmosphere, including iron, magnesium, and other metals that exist in gaseous form due to the extreme temperatures. These detections provide direct evidence for the exotic chemistry operating under conditions where traditional distinctions between solid, liquid, and gas phases become meaningless. The orbital evolution presents intriguing questions about long-term stability in such extreme stellar environments. Tidal interactions with the massive hot parent star gradually alter the orbital characteristics, while stellar evolution changes the radiation environment over millions of years. These combined effects likely drive ongoing changes in planetary properties and atmospheric behavior. Thermal emission from this object makes it one of the brightest known exoplanets in infrared wavelengths, allowing detailed spectroscopic studies of its atmospheric composition and temperature structure. These observations reveal atmospheric layers with different temperatures and chemical compositions, providing insights into heat transport and circulation patterns operating under extreme conditions. The lifetime of this planet remains uncertain due to the ongoing atmospheric escape and the rapid evolution of its parent star. The massive hot star will exhaust its nuclear fuel relatively quickly compared to smaller stars, potentially altering the radiation environment before the planet loses its entire atmosphere to space. This creates a race between stellar evolution and planetary atmospheric loss. Comparative studies between this world and other ultra-hot Jupiters reveal common characteristics among worlds experiencing extreme stellar heating. These comparisons help identify universal processes operating in high-temperature planetary atmospheres, while highlighting unique features that depend on specific stellar and planetary properties. The study of this extreme system provides valuable insights into atmospheric physics under intense conditions and helps refine theoretical models of planetary atmosphere behavior at temperatures approaching stellar values. The planet serves as a natural laboratory for testing theories about matter behavior under conditions difficult to replicate in terrestrial experiments. Cloud formation processes here, if they occur at all, would involve exotic materials condensing at temperatures far higher than any clouds found in our solar system. Potential cloud materials might include vaporized metals and refractory compounds that condense and evaporate in complex cycles driven by atmospheric circulation patterns. The discovery and characterization of this ultra-hot gas giant demonstrates the remarkable diversity of exoplanetary environments and the extreme conditions under which planetary systems can exist. This world expands our understanding of planetary science and challenges traditional models of planetary formation and evolution. Future observations using advanced space telescopes may reveal additional details about atmospheric structure, chemical composition, and dynamic behavior. These studies will contribute to broader understanding of planetary atmospheres under extreme conditions and help identify similar worlds throughout the galaxy. The ongoing study of this hot giant represents humanity's effort to understand the full range of planetary environments that exist around other stars. This extraordinary world demonstrates that planets can survive and maintain complex atmospheric processes even under conditions that approach the extreme environments found in stellar atmospheres. Technological advances in exoplanet characterization continue to provide new insights into ultra-hot worlds like this. Each observation contributes to our growing understanding of planetary physics, atmospheric chemistry, and the remarkable diversity of worlds that populate our cosmic neighborhood. This planet stands as one of the most extreme examples of planetary evolution under intense stellar radiation, representing a world where the boundaries between planetary and stellar physics become increasingly blurred. This remarkable object continues to challenge our understanding of what constitutes a planet and expands our appreciation for the incredible variety of worlds that exist throughout our universe. Gliese 436, b, the burning ice planet. In the constellation Leo, approximately 33 light-years from Earth, orbits one of the most paradoxical worlds ever discovered. This burning ice planet presents a contradiction that challenges our everyday understanding of matter and physics. Existing as a planet composed largely of water ice that maintains temperatures exceeding 400 degrees Celsius. This extraordinary world demonstrates how extreme pressure can create states of matter that defy conventional expectations, earning it recognition as one of the most scientifically fascinating exoplanets known to astronomy. The planet maintains an orbital period of 2.64 Earth days, circling its red dwarf parent star. At a distance closer than Mercury orbits our Sun. This proximity subjects the world to intense stellar radiation that would normally vaporize any water present on or within it. However, the extreme internal pressures created by its substantial mass transform water into exotic forms that remain solid despite the scorching temperatures. This Neptune-sized object possesses a mass approximately 23 times that of Earth, placing it firmly in the category of intermediate mass planets. This substantial mass, concentrated within a radius only about 4 times larger than Earth's, creates gravitational forces strong enough to compress water ice into crystalline structures that can withstand temperatures far exceeding the normal melting point of ice under terrestrial conditions. The concept of hot ice exists due to the complex relationship between temperature, pressure, and the behavior of water molecules. Under the extreme pressures found within this body's interior, water molecules arrange themselves into dense crystalline lattices that remain stable at temperatures that would instantly vaporize ice under normal atmospheric pressures. This creates a solid form of water ice that can exist at temperatures approaching 1,000 degrees Celsius. The internal structure likely consists of a rocky core surrounded by thick layers of various forms of high-pressure ice, topped by a substantial hydrogen and helium atmosphere. The different pressure zones create environments where multiple forms of exotic ice coexist, each stable under specific combinations of temperature and pressure conditions found at different depths. Atmospheric composition studies reveal that this world maintains a substantial gaseous envelope dominated by hydrogen and helium, with traces of water vapor, carbon monoxide, and methane. The presence of these atmospheric components confirms its Neptune-like characteristics, while providing insights into the chemical processes operating under the extreme conditions found in this unusual environment. The formation history likely involved accretion of water-rich materials in the outer regions of its planetary system, followed by inward migration to the current close orbit. This migration scenario explains how a water-rich world could end up so close to its parent star, while retaining the massive ice layers that define its unique characteristics. Thermal evolution models suggest that the interior continues to radiate heat generated during formation and migration processes. Elevated internal temperatures persist due to gravitational compression, radioactive decay, and ongoing structural adjustments as different forms of ice transition between various high-pressure phases in response to changing internal conditions. The parent star represents a typical red dwarf, smaller and cooler than our Sun, but capable of maintaining stable energy output over time scales much longer than solar-type stars. This M-type star provides the external heating that maintains the planet's surface temperatures, while the internal pressure gradients preserve the solid ice phases that give it its paradoxical nature. Tidal forces from the nearby star likely influence the internal structure and may contribute to heating through tidal flexing of the ice layers. These gravitational effects could drive ongoing geological processes within the high-pressure interior, potentially creating convection patterns and phase transitions that affect overall thermal evolution. The various forms of ice present include exotic phases designated as Ice 7, Ice 10, and potentially even more extreme forms that exist only under the most intense pressure conditions. Each of these ice phases possesses different crystalline structures, densities, and thermal properties, creating a complex internal architecture unlike anything found in our solar system. Magnetic field generation depends on the electrical conductivity of the internal layers and the presence of convective motions within the structure. The high-pressure ice layers might exhibit electrical properties different from conventional ice, potentially contributing to magnetic field generation through mechanisms not found in terrestrial planets. Atmospheric escape processes gradually remove material from the outer atmosphere due to stellar heating and the planet's relatively strong gravitational field. However, the substantial mass allows it to retain most of its atmospheric envelope over astronomical timescales, maintaining the surface pressures necessary to preserve the exotic ice phases in its interior. The study of phase transitions within this world provides insights into water behavior under extreme conditions that cannot be easily replicated in laboratory experiments. It serves as a natural laboratory for studying the properties of matter under pressure and temperature combinations that push the boundaries of current scientific understanding. Seismic activity within the high-pressure ice layers could create phenomena unlike any geological processes found on rocky planets. The transitions between different ice phases, driven by pressure and temperature variations, might generate internal movements and energy releases that reshape the internal structure over geological timescales. Comparative studies with other Neptune-sized exoplanets help identify the range of internal structures and compositions possible for intermediate mass planets. These comparisons reveal that worlds with similar masses can exhibit dramatically different characteristics depending on their formation, histories, and current environmental conditions. The detection and characterization of this burning ice body represents significant advances in exoplanet science, demonstrating our ability to determine detailed properties of distant worlds through precise measurements of their orbital characteristics, atmospheric composition, and thermal emission. These observational capabilities continue to reveal unexpected phenomena that expand our understanding of planetary physics. Climate modeling efforts must account for the complex interactions between stellar heating, atmospheric circulation, and the thermal properties of the exotic interior composition. These models help predict surface conditions and atmospheric behavior while testing our understanding of heat transport in environments dominated by high-pressure ice phases. The long-term stability of this unusual internal structure depends on the balance between stellar heating, internal heat generation, and the thermodynamic properties of various ice phases. Changes in any of these factors over astronomical timescales could trigger transitions between different internal configurations, potentially altering the overall characteristics. Future observations using advanced spectroscopic techniques may reveal additional details about atmospheric composition, internal structure, and thermal properties. These studies could provide direct observational evidence for theoretical predictions about the behavior of water under extreme conditions. The ongoing research surrounding this paradoxical planet contributes to broader understanding of planetary interiors, phase transitions, and the range of physical conditions that can exist within exoplanetary systems. This exotic world demonstrates the remarkable diversity of planetary compositions and the unusual states of matter that can exist under conditions different from those found on Earth. Technological developments in high-pressure physics and materials science benefit from the natural experiments provided by worlds like this. The extreme conditions found within it offer insights into material behavior that inform both theoretical understanding and practical applications of high-pressure physics. This world continues to challenge our understanding of planetary science and the behavior of familiar materials under unfamiliar conditions. It serves as a reminder that the universe contains environments where the conventional rules of physics create outcomes that seem impossible, but represent perfectly natural consequences of extreme conditions. The paradoxical nature of this burning ice planet expands our appreciation for the incredible diversity of worlds that exist throughout our galaxy, demonstrating that planets can maintain internal structures and compositions that defy everyday experience while operating according to well-understood physical principles under extreme conditions. I hope you enjoyed this journey. If you're still awake, there's another fascinating space adventure waiting for you right here on the screen. Thanks for watching. See you in the next video, and have a good night.